In this video, we'll explore Amazon Web Services. Amazon Web Services is a comprehensive collection of infrastructure services, including compute, storage, database, and networking services. AWS also provides essential platform capabilities like mobile services, analytics, and machine learning. All these services and platform capabilities are offered on a pay-as-you-go pricing basis. In order to use AWS, you need to sign up for an account. So you provide contact information and a payment method. Now, even though you do need to provide a payment method, many of the services are offered under the AWS free tier, so you can experiment and play with AWS free tier services without charge. Under the free tier, AWS also provides some usage alerts automatically, so you are always aware of and can recognize potential charges. You can also create additional alerts under AWS budgets. Once you've created an account, you sign into the AWS Management Console with what is known as the root user account. This is the account you create when you sign up for an AWS account. The AWS Management Console is a web-based interface into all the AWS services and capabilities. Through the Management Console, you can create, configure, and monitor all of your AWS resources on your account. AWS software development kits are available for most programming languages, including Java, .NET, JavaScript, PHP, Python, and others. Software development kits allow us to interact with AWS services from our code. There are also a number of specialty software development kits. For example, the AWS Mobile SDK for building mobile applications that access AWS services, and the AWS Internet of Things Device SDK for writing applications that access the AWS Internet of Things platform. AWS also provides some powerful interactive tools to build with. The AWS Command Line Interface, or CLI, is a tool for managing AWS resources from the command line. It's available for different operating systems, including Windows, Linux, Unix, and Mac OS. There is also a version of AWS tools for PowerShell if you'd prefer to use PowerShell instead of the CLI. In this video, we'll explore AWS Authentication and Authorization. First, a quick review. Authentication involves the method or action used for verifying the identity of a user or a process. Authorization is the process of determining the access level to be granted to an authenticated user or process to various resources like files, services, applications, data, and others. AWS can be used as an identity provider, which entails storing identities and providing the method used for authentication. This applies to AWS services, to applications residing on AWS infrastructure, and applications that run on non-AWS infrastructure like web and mobile applications. Benefits related to using AWS as the identity provider include the fact that it's a managed service. So all the heavy lifting required to deliver identity provider services is performed by AWS. It also eliminates single points of failure. It's highly available, scalable, and AWS offers several tools for managing, controlling, and auditing the identity provider service, like Amazon CloudWatch and AWS CloudTrail. When we're talking authentication and authorization on AWS, we need to consider AWS planes of access. There are two planes of access involved in managing and accessing AWS services. There's a control plane and a data plane. The control plane allows access in order to perform operations on specific AWS instances. AWS manages access to the control plane via AWS API operations. The data plane allows access to applications running on AWS infrastructure. The data plane controls access to sign into AWS compute instances and change the guest OS configuration or make changes to an application on the compute instance. Connection to Ec2 instances is achieved using Secure Shell or Remote Desktop Protocol. Although these different planes use different paths, protocols, and credentials, for many AWS services, the two planes are identical. AWS identity refers to the authenticated user or process, while authorization defines what that user or process can do. Authorization is established with user-executed APIs. Operations and tasks are performed via these APIs. Policies related to access are JSON documents with attributes described as key value pairs. You may hear them referred to as attribute value pairs. Now, each policy needs at least 3 attribute key value pairs: effect, action, and resource. Effect can be either allow or deny. The entity in question, which could be a user, group, or role, is either granted or denied permission to execute the associated API. Action defines whether the API is allowed or denied. Actions can be determined by individual API or by grouping APIs for the same service with a wildcard. And resource defines where the API is allowed or denied. One example is with Amazon S3. The execution of an API can be permitted against a particular bucket, an object, or a group of objects. In this video, we'll explore AWS Federation. Federation allows us to centrally manage access to our AWS resources. With Federation, we can implement single sign-on to access our AWS accounts with credentials from our corporate directory. Federation uses open standards like the Security Assertion Markup language to exchange identity and security information between an identity provider and an application. There are 2 components that work together to create a federation. The identity provider stores identities and provides authentication and authorization. An identity provider can be seen as part of the process that answers the question, who are you? An identity consumer is the component that stores a reference to the identity. An identity consumer provides very granular authorization. Due to the trust relationship established between identity provider and consumer, the identity consumer trusts the answer to the question, who are you, supplied by the identity provider, and grants access based on the identity. Federation with AWS allows us to use AWS as an identity provider to secure access to both AWS and non-AWS resources alike. And we can also use a non-AWS resource like SAML, OpenID Connect, or Active Directory as the identity provider in order to facilitate single sign-on. AWS Federation can facilitate various mechanisms, including the custom-built identity provider, which was the original approach used by AWS for Federation. Federation with AWS also allows cross-account access, which means that we can access resources across multiple AWS accounts with a single set of credentials. Users can be granted access to resources within company accounts, and we don't have to maintain multiple user entities and passwords. Security Assertion Markup language provides federation between an identity provider and a service provider, and this is an option when a trust relationship has been established between the identity provider and the service provider, and you are in an AWS account. The identity provider and the service provider exchange metadata using an XML formatted document. This metadata contains the certificates and attributes that define the trust relationship between the identity provider and the service provider. All ensuing authentication and authorization occurs between the user and the identity provider. Assuming a successful authentication and authorization, the identity provider makes the assertion to the service provider, and because of the already established trust relationship, the service provider recognizes the assertion and grants access. SAML can also interface with Amazon Cognito to manage access to non-AWS cloud services. OpenID Connect supersedes SAML. It's easier to configure than SAML and employs the use of tokens rather than assertions to provide access. With OpenID Connect, the OpenID provider uses a relying party trust for tracking the service provider. The OpenID provider and relying party exchange metadata, with the OpenID provider passing information regarding the location of its endpoints to the relying party. All authentication and authorization takes place between the user and the OpenID provider, with the OpenID provider issuing a token to the service provider. OpenID Connect has 3 different types of tokens. The ID token establishes a user's identity, an access token provides access to APIs, and the refresh token allows one to obtain a new access token to replace an expired one. Microsoft Active Directory is a common identity provider. Active Directory Forest trusts can be used to establish trust between an Active Directory domain controller and AWS Directory Service for Microsoft Active Directory. The domain controller may be on-premises or in the AWS cloud. You can configure AWS Single Sign-On service to work with Active Directory to manage single sign-on access. Users can sign into the AWS Single Sign-On user portal with existing corporate credentials to obtain AWS CLI credentials from one central location. The AWS CLI credentials obtained this way are only good for 60 minutes. AWS Single Sign-On can also be used to manage AWS accounts through AWS organizations. Permissions may be assigned, for example, based on typical job function, and these permissions may be customized and tailored to an organization's security requirements. AWS Single Sign-On also integrates with Active Directory via Directory Service. This allows one to sign in to the user portal using their existing corporate Active Directory credentials. AWS Security Token Service creates and provides trusted users with temporary security credentials to get access to AWS resources. Temporary security credentials are similar to long-term access key credentials, but there are some differences. Temporary credentials consist of an access key ID, a secret access key, and a security token, and they can be configured to remain valid from minutes to several hours. Once the credentials expire, AWS no longer recognizes them. Amazon Cognito is a managed service for handling sign-in and permissions for mobile and web applications. Amazon Cognito integrates with AWS Security Token Service to identify users and provide them with a consistent identity over the lifetime of an application. Since many organizations already have Microsoft Active Directory implemented as their identity store, it's very convenient to integrate Amazon Cognito with Microsoft Active Directory as the identity provider rather than configuring a new identity store. We can implement Microsoft Active Directory on AWS by running Active Directory on an Amazon EC2 instance. We can use Active Directory Connector to connect AWS services with an existing on-premises Microsoft Active Directory. We can also implement Microsoft Active Directory on AWS by creating a simple Active Directory, or Simple AD. Simple AD is a Microsoft Active Directory that provides compatibility with AWS directory services. And we can implement Active Directory on AWS by deploying AWS Managed Microsoft Active Directory, which is an actual Microsoft Windows Server Active Directory implementation managed by AWS on AWS infrastructure. It supports AWS managed applications and services, including Amazon Workspaces, WorkDocs, Amazon QuickSight, Amazon Chime, Amazon Connect, and Amazon RDS for SQL Server. In this video, we'll explore the AWS Management Console. The AWS Management Console is a web-based application that encompasses a set of service consoles for managing Amazon Web Services. When you sign in to AWS, you're directed to the Management Console homepage. From the homepage, you can access the service consoles, which are comprised of tools for working with different AWS resources, including Amazon S3 buckets, launching and connecting to Ec2 instances, configuring Amazon CloudWatch alarms, and to retrieve information about your AWS account, including billing information. There are multiple ways to navigate to the various individual service consoles. You can search for a service using the Find Services search box. You can enter names, keywords, or partial acronyms, and a list of matching results appears from which you can choose your desired service console. You can also choose a service that you've recently visited in the Recently Visited Services area located below Find Services. You can also choose services to open a full list of services with options to list services by category or alphabetically. Other features of AWS Management Console include the ability to choose a region to specify where to deploy resources and subsequently where to manage those resources, access to billing information, search for and access comprehensive documentation, forums, and other resources for troubleshooting and finding solutions to common issues. The AWS Management Console is also compatible with various devices, including tablets and phones. The Management Console is also available as a mobile app from the Amazon App Store, from Google Play, or from iTunes. You can also change your password on the AWS Management Console by selecting your account and choosing Security Credentials. And you also have the ability to create and remove shortcuts to frequently used service consoles. In this video, we'll explore AWS accounts. The account that you create when you sign up for AWS is the root account. You can use the AWS root account to manage your AWS resources and services. But remember that the AWS root account gets root permissions to all AWS resources and services. So obviously, the root account is very powerful, but with that power comes a lot of accountability. You should never use the root account for day-to-day interaction with AWS. In fact, this account is so important that when you sign up, Amazon automatically deletes the root account access keys for you. You can change the account name, the root user password, and the root user email address associated with an AWS account. To do so, you sign into the AWS Management Console, and on the navigation bar, you choose your account name and then choose My Account. From there, on the Account Settings page, you choose to edit whichever settings that you're going to edit. You can also change the contact information associated with an account, including mailing address, telephone number, website address, and others. To edit your contact information, you basically sign into AWS Management Console, and on the navigation bar, choose your account name and then choose My Account. And under Contact Information, choose Edit. For the fields to change, enter your updated information and then choose Update. You can add an email address for billing in the Alternate Contact section to have AWS send a copy of billing-related emails to that email address. You can change the local currency associated with your account. To do so, again, you sign into the Management Console, and on the navigation bar, choose your account name and then choose My Account. Scroll down to the Payment Currency Preference section, and next to Payment Currency Preference, choose Edit. For Select Payment Currency, select the currency to pay your bill in, and then choose Update. Alternate contacts enable AWS to contact another person regarding issues with your account. To add, modify, or delete alternate contacts for an account, we need to sign into AWS Management Console, and on the navigation bar, choose your account name and then choose My Account. Scroll down to the Alternate Contacts section and choose Edit. And for the fields to change, enter your updated information and then choose Update. And with that, you now have an alternate contact that can be notified if there's an issue with the account. Now, you can also use multiple AWS accounts, and this requires a particular strategy. So you want to design your AWS account strategy in order to maximize security, but also to align with your business and governance requirements. So for example, we have a business requirement of centralized security management. Well, this would require a single AWS account. And with that, you centralize information security management, and you also minimize overhead. Next, you have separate environments, for example, production, development, and testing. So this would require 3 AWS accounts. So you would create one AWS account for production, one for testing, and one for development. Another use of multiple AWS accounts is for different departments, particularly different autonomous departments. For this, you would create an AWS account for each one. Then you can assign permissions and policies under each account. Next, we have independent projects. For this, you would create multiple AWS accounts, starting with a single AWS account for common project resources like DNS services, Active Directory, and so on. Then for the independent projects, you create a separate AWS account per project. You can assign permissions and policies under each project account and grant access to resources. You can also configure a consolidated billing relationship across multiple accounts, which will ease the complexity of trying to manage a different bill for each of the separate accounts. In this video, we'll explore identity and access management. With identity and access management, or IAM, you can create multiple users. Each user has their own individual security credentials, all centrally controlled and managed under one single AWS account. IAM users aren't necessarily people. Rather, an IAM user can be a person, service, or an application that requires access to AWS resources through the Management Console, the CLI, or from one of the many APIs. An IAM user can also be allocated with appropriate permissions in order to create new IAM users or manage and delete existing users. Now, IAM groups consist of multiple IAM users under one account and may be created for various reasons. For example, perhaps you have users that you would like to group based on functional aspects, maybe organizational requirements, or it could be a geographical basis. It could also be by project or any other basis where IAM users require access to similar AWS resources in order to complete their jobs. Each IAM group is provided with permissions to access AWS resources by assigning one or more IAM policies to the group. Policies assigned to an IAM group are inherited by IAM users belonging to that group. Even if there is only one user that requires access to a specific resource, AWS security best practice dictates that you should identify or create an AWS group to provide that level of access. So you provision user access through group membership with permissions and policies assigned at the group level. Each AWS account or Iam user represents a distinct, unique identity with unique long-term credentials. There are two main credential types associated with these identities. Those used for sign-in to the AWS Management Console and those used for programmatic access to the AWS APIs. So AWS credentials include username and password. Usernames for AWS accounts are always email addresses, while IAM usernames allow for more flexibility. Your AWS account password can be anything you define. IAM user passwords can be forced to comply with a policy that you can define. For example, minimum password length, the use of specific characters, and so on. AWS multi-factor authentication offers an extra layer of security for sign-in credentials. With multi-factor authentication enabled, when users sign into an AWS website, they will be prompted for their username and password, as well as for an authentication code from their multi-factor authentication device. You can also require multi-factor authentication for users in order to delete S3 objects. In certain circumstances, you may need to delegate access to users or services that don't typically have access to your AWS resources. Common use cases for delegating access this way includes applications running on Amazon EC2 instances that require access to AWS resources. For example, Amazon S3 buckets. For cross-account access, in order to manage access to resources across multiple AWS accounts. And for identity federation. Some users may have identities outside of AWS, for example, in the organization's corporate directory. Those users may need to work with AWS resources or with applications that access AWS resources. These users also need AWS security credentials in order to make requests to AWS. In each case, IAM roles and temporary security credentials can be used to accommodate these use cases. An IAM role allows us to define a set of permissions to access AWS resources needed by a user or service, but the permissions are not attached to a particular IAM user or group. Rather, IAM users, mobile, and EC2-based applications as well as AWS services can programmatically assume a role. Assuming the role causes temporary security credentials to be returned, and the user or application may use those credentials for programmatic requests to AWS. In addition, these temporary security credentials can be set to expire as necessary, and they are automatically rotated. IAM roles for Amazon EC2 is a specific type of IAM role implementation that resolves the use case where applications running on Amazon EC2 instances require access to AWS resources. For example, consider a developer running an application on an Amazon EC2 instance that must have read-only access to an Amazon S3 bucket. An administrator can create a suitable role, which includes policies that grant read permissions for the bucket and allow the developer to launch the role with an Amazon EC2 instance. The administrator does not have to grant the developer permission to access the bucket, and further, the developer does not have to share their credentials. So here's how that works. An administrator uses IAM to create a suitable role. In the role, the administrator specifies a policy where only EC2 instances can assume the role, and the policy also specifies only read permissions for the S3 bucket. Subsequently, a developer launches an Amazon EC2 instance and associates the new role with that instance. When the application runs, it retrieves credentials from the instance metadata on the Amazon EC2 instance, and then using role credentials, the application accesses the S3 bucket with read-only permissions. We can use Iam roles to provide cross-account access by enabling Iam users from a different AWS account to access resources within our AWS account, thereby sharing access to resources. To establish cross-account access, in the trusting account, we create an Iam policy that grants the trusted account with access to specific resources. The trusted account may then delegate this access to its Iam users. We can use Iam roles to address the identity federation use case by creating an identity broker between our corporate users and our AWS resources that effectively manages the authentication and authorization without having to recreate all the users as Iam users in AWS. In this scenario, the enterprise user accesses the identity broker application. The identity broker application authenticates the user against the corporate identity store. The identity broker application has permissions allowing it to access the AWS Security Token Service to request temporary security credentials. And now, enterprise users can access AWS APIs or the AWS Management Console. In this video, we'll explore AWS regions and availability zones. AWS operates in multiple regions around the world, a truly global infrastructure. AWS regions are located in separate geographical areas, and furthermore, each region maintains its own isolated copies of AWS services. Each AWS region comprises multiple data centers which are grouped together to form availability zones. Regions are composed of multiple availability zones, and this enables AWS to provide highly available services. Availability zones are physically separated from each other and are designed to operate in an isolated manner, independent of each other, again, addressing the need for highly available, resilient services. Keep in mind that though they are physically separated, availability zones are connected by low latency, high throughput redundant networking. With this infrastructure, AWS customers can improve the resilience of their applications by deploying a copy to a second availability zone within the same region. The application can then remain available to users even in the event of a disruption affecting an entire data center. Note that many of AWS services automatically replicate data across multiple availability zones within an AWS region to provide high availability, resilience, and durability. Many AWS services expose regional API endpoints for consumption. While dispatching web service calls to regional endpoints, the region is commonly identified in the URL. API calls to a regional endpoint typically only affect those resources within the specific AWS region corresponding to the endpoint. When working with AWS services, the AWS Management Console refers to regions quite differently from the parameters that are used with AWS CLI and the software development kits. For example, US East, North Virginia, in the AWS Management Console is US-East-1 with the CLI and the SDK. US West Oregon is US West 2. EU London is EU-West-2. And Asia Pacific Tokyo is AP-Northeast-1. Now, there are also AWS services such as Iam, the Identity and Access Management Service, that aren't limited to a single region. When you interact with these services in the console, the region selector in the upper right-hand corner of the console displays the word global. So the API endpoint for Iam is the same regardless of region. So in US East, North Virginia, US East, Ohio, US West, North California, in any region, the Iam service API endpoints are at iam.amazonaws.com. Choosing a region is an important consideration, and one factor when choosing an AWS region is the availability of the services that are going to be required by your organization and your applications. Other aspects to consider when choosing a region include latency, of course the cost, as well as data residency. With respect to service availability, we need to choose a region that has all, or at least most of the services that we require and intend to use. Each region exposes its own AWS Cloud Service endpoints, and not all AWS services are available in all regions. With respect to proximity and latency, it's a smart idea to choose a region closer to the application users, on-premises servers, or other workloads. This allows us to decrease the latency that's going to be involved when making API calls. When I refer to data residency, I mean to choose a region that allows us to stay compliant with any regulatory or business contractual requirements in order to store data within a specific geographical region. Business continuity is another consideration. We should choose a pair of regions based on any specific requirements regarding data replication for disaster recovery. For example, we can select a second AWS region as a target for replication of data based on its geographical distance from the primary AWS region. And price or cost. AWS service prices are on a per region basis. So we should consider cost, but not by sacrificing service availability and latency. In this video, we'll register an account on AWS, and the objective here is to recognize how to complete the sign-up process for an account on AWS. To start, open a browser and navigate to console.aws.amazon.com. At the bottom of the sign-in page, locate and click on the Create a New AWS Account button. This brings you to the Create an AWS Account page. So here you'll enter the relevant information like email address, password, confirm password, and an AWS account name. Now, this AWS account name is useful if you want the URL for your sign-in page to contain an easily recognized identifier like your company name instead of your 12-digit AWS account ID. Amazon also refers to this as an account alias, and the account alias must be unique across all Amazon Web Services products, and it must contain only digits, lowercase letters, and hyphens. When you're done filling in the information, click the Continue button. This brings you to the Contact Information page. Now here you're going to enter your contact information and an account type. For an account type, just leave Professional, the default, selected. Currently, the full name field has your account name in it. You'll replace that with your full name and the company name and the rest of the contact information. Then you arrive at the bottom where there's a check here to indicate that you have read and agreed to the terms of the AWS Customer Agreement checkbox. At this point, I like to print a copy of the customer agreement. And to do that, I'll middle mouse click the AWS Customer Agreement hyperlink beside the checkbox. That will open up the customer agreement in a new tab. Navigate to the new tab, and now click the menu icon for your browser, locate Print, select it, and a print preview page opens. Click Print. That opens the print dialog. I'm just going to select Microsoft Print to PDF option and click Print. Now I'll save it to my default location, which is the desktop, with the name AWS Customer Agreement in the file name field, then click Save. Okay, now that that's done, close the preview, close the AWS Customer Agreement tab. Now back on the AWS Contact Info page. Now you can click the checkbox beside Check Here to indicate. Then click the Create Account and Continue button, located just below. Now you'll enter your payment information. Now keep in mind that you do have 12 months of free tier access, and the credit card is simply for identification purposes only, and will not be billed as long as you stay within the free tier resources. So enter the credit card information, then click Verify and Add. Now on the Confirm Your Identity screen, I'm going to have Amazon send me a verification code by text message, so I'll leave text message SMS selected as the default. I'll enter my cell phone number and the security check and click Send SMS. Now on the Enter Verification Code dialog, I'll enter the verification code that I received on my phone. Click Verify Code. And with that, my identity has been verified successfully. So I'll click Continue. Now, to select a support plan, I'm just going to select a basic plan, so I'll click Free. There are developer plans, business plans, and others as well, but we'll select Free for now. This brings me to the Welcome to Amazon Web Services page. I'll click Sign In to the console. Now back on the Sign In page, I'm going to log in with my root user account. That's what I just registered. So I'll enter my root user email address. Click the Next button just below it. Now I'll enter my password, and I'll click Sign In. And I've successfully signed into AWS Management Console. So I've successfully registered an AWS account. In this demo, we'll manage Iam users. The objective here is to create an Iam administrative user and manage that user's permissions with groups. Okay, to get started, open a browser and in the address bar, type console.aws.amazon.com. Press enter. This brings us to the sign-in page. The root user is selected. We'll specify the root user email address. Click Next. And the password. And click Sign In. Okay, so we're signed into the AWS Management Console. To manage Iam users, we need to go to the Iam Management Console. And there's a couple of ways that we can do that. Up in the menu bar, we can click the down arrow beside Services, and we'll find Iam under Security, Identity, and Compliance. We can also search by entering the service or a part of it in the Find a Service by Name or Feature field. Let's collapse this by clicking the up arrow now. We can also find the service by entering names, keywords, or acronyms right here on the AWS Management Console homepage. So in this field, I'll type Iam. I'll click the Iam link. That brings us to the Iam Management Console. Note in the Iam Management Console, the Iam user's sign-in link. It's still using the 12-digit code for the sign-in link. I'll click Customize to the right of the Iam user sign-in link. And in the Create Account Alias dialog that appears in the Account Alias field, I'll type a new account alias. And I'll click Yes, Create. So now Iam users can use this link to sign in. Notice that we also have 2 roles created under Iam resources, but no other resources at this point. And those roles are created when we create the AWS account. That's the service role for support and the service role for trusted advisor. Let's click the dashboard in the left menu to go back. And under security status, we have 1 out of 5 tasks completed. The first task is to delete our root access keys. Now, Amazon automatically removed my root access keys because those keys provide unrestricted access. So instead, from a security perspective, it's important to realize that you must use Iam accounts on AWS, not the root account. So when you're setting up services, you're setting up websites, you're setting up whatever types of resources, you're going to be using Iam accounts. And you can set up an Iam admin account, for example, with privileges that are tied to an admin group. So let's do that. So let's set up our first Iam user. In the left-hand menu, we'll click Users. We'll click Add User. I'll specify a username. And under Select AWS Access Type, I'll click the checkbox beside Programmatic Access. And we'll also provide AWS Management Console access, so I'll click that checkbox. Then the console password setting appears. By default, auto-generated password is selected. We'll leave that as is. And require password reset appears as well. And that checkbox is checked. And this means that the user must create a new password at the next sign-in. And notice that they automatically get the Iam user change password policy, and that allows them to change their own password. So let's click Next Permissions. All right, so here we can attach existing policies directly by clicking Attach Existing Policies Directly, and then we simply select the policies that we want from the list of policies that appear. In reality, that is a really poor way to manage users. It's not scalable, it's not manageable. So instead, let's click Add User to Group. We don't have any groups yet, so we'll click Create Group. In the group name field, I'll type admins, and in the list of policies, the very first policy is administrator access. I'll click the checkbox beside that, and then I'll click Create Group. This brings us back to the Add User page with set permissions, and that user has now been added to the admins group. So let's click Next Tags. Now tags are optional. These are key value pairs that we can use to organize users, to track users, to control access. Now, again, this is optional, but I'm going to specify a title key, and the title for this user is Senior Developer. So under Key, I'll type Title. Under Value, I'll type Senior Developer. Click Next Review. Now this gives us a chance to review the settings before we click Create User. And that's all good. So let's click Create User. Now the user has been created. And at this time, we're going to download the credentials CSV. So click the download.csv button. And in the opening credentials.csv dialog that appears, make sure that Save File is selected and click OK. All right, now that downloads our credentials. And we really need to be careful with those credentials. And in fact, we should either encrypt that data or put that credentials.csv file in a vault somewhere. Now, if you end up losing that credentials.csv file, you'll have to come back here and recreate the credentials. And now for the password, I'm going to click Show. And I'm going to right-click the password and select Copy. That's the auto-generated password. Okay, so now let's close. And now our user has been created. So we can actually log in. But let's go back to the dashboard again. And note that under security status, we have 3 out of the 5 tasks complete. We're going to click the down arrow beside Apply an Iam password policy, then click Manage Password Policy. Then near the top of the page, we'll click Set Password Policy. This brings us to the Set Password Policy page where we have a number of rules that we can apply. We'll click the checkbox beside Require at least 1 uppercase, Require at least 1 lowercase, Require at least 1 number, and Require at least 1 non-alphanumeric character. Now click Save Changes. And the password policy has been updated. Let's go back to the dashboard again and see that we now have 4 of our 5 tasks completed. We're not going to activate multi-factor or MFA authentication on the root account in this demo, so that won't get checked off here. But we have 4 out of the 5 checked off at this point. And now we're ready to sign in as the Iam user. Now we can use the Iam User's sign-in link to sign in at this point. So if I highlight this and copy it and paste it, then I can sign in that way. But then the password that I just copied from the new user that we created won't be usable. So instead of doing that, I'm going to click the account in the menu bar, and I'm going to click sign out. Then in the address bar, I'm going to again type console.aws.amazon.com. And again, this brings us to the sign-in page. This time we're going to click Iam User. We can specify the account ID or the account alias. I'll specify the account alias. It's much easier to remember. I'll click Next. And now I'll specify the Iam username that I created. I'll paste the password in that I copied. So I'll press Ctrl-V to paste that in. Then I'll click Sign In. This brings us to the Change Password page. So we have to enter a new password. So in the old password field, I'll Ctrl-V to paste that old password in. In the new password field, I'll specify my new password, and I'll retype my new password. Press Confirm Password Change, and there we are. We've successfully created the Iam administrative user, and we've signed in as the Iam administrative user. In this video, we'll implement multi-factor authentication on AWS. To get started, I've opened my browser and I've navigated to aws.amazon.com. To go to my account, I'll click My Account, and then I'll click AWS Management Console. On the sign-in page, root user is the default selection, so I'll specify my root user email address. Click Next, enter my password, and click Sign In. And now I'm on my AWS Management Console homepage. I'm going to go to the Iam dashboard by clicking Iam under Recently Visited Services. Now on the Iam dashboard, under Security Status, I have 4 out of 5 tasks completed. I still have to activate multi-factor authentication, or MFA, on my root account. So I'll click the down arrow beside Activate MFA on your root account, and I'll click Manage MFA. This brings me to my security credentials page, where I'll expand multi-factor authentication by clicking the up arrow, and I'll click Activate MFA. Now on the Manage MFA Device dialog, we choose the type of MFA device to assign. I'm going to choose the virtual MFA device, and this refers to an authenticator app that's installed on my mobile device. So I'll leave virtual MFA device selected and click Continue. Now on the Setup Virtual MFA Device dialog, in step 1, it asks to install a compatible app on your mobile device or computer. Now you can see a list of compatible applications by clicking the List of Compatible Applications hyperlink. Now in step 2, I'm going to use my virtual MFA app and my device's camera to scan the QR code. So I'll click Show QR Code, and I'll scan the QR code. Now I'll scroll down, and I'll enter the 2 consecutive MFA codes that I receive. The first one arrives, then the second one, and now I'll click Assign MFA, and the Setup Virtual MFA Device dialog appears, telling me that I've successfully assigned a virtual MFA device. So now I'll click Close to close the dialog, and now I'll click my account and I'll click Sign Out, and now I'll log back in. So I can do that by clicking Log Back In, or I can also go back to my account and choose AWS Management Console again. So I'll do that. And now with the root user still selected as the option, I'll enter the root user email address and click Next. My password and click Sign In. And now I'm asked for an authentication code, my MFA code. So in the MFA code field, I'll enter the authentication code that I received, click Submit, and I'm in. So now if I go back to my IAM dashboard, I'll see that all 5 tasks under security status have now been completed. So I've successfully implemented multi-factor authentication on AWS. In this course, we've examined AWS Identity and Access Management, or IAM, and how it's used to manage and secure access to AWS resources and services. We did this by exploring the resources and services offered by AWS, how authentication and authorization are managed on AWS. We explored the AWS Management Console for managing services and the use of AWS accounts and their management. We also explored Iam users, groups, and roles, and AWS regions and availability zones. We went on to explore how to register an account on AWS, how to create an IAM administrative user, and manage IAM users with groups and roles. And we also explored how to enable and configure multi-factor authentication with AWS. In our next course, we'll move on to explore how to work with the Amazon Elastic Cloud Compute Service, including the use of elastic block storage volumes, security group management, and IP configuration. In this video, we'll explore Amazon Elastic Compute Cloud. Amazon Elastic Compute Cloud, which I'll refer to as EC2 from here on, is a service on AWS that allows us to provision resizable computing environments. Referred to as instances, we can choose the hardware resources we need, the operating system, as well as the software that we want running on the instance. EC2 instances are provisioned on a host machine in a specific availability zone. And typical EC2 instances are virtualized computing environments with virtualized access to host machine resources. On the host, there can be multiple isolated guest environments running and sharing the same resources from the host machine. In addition, there are some EC2 instance types that provision bare metal access, which essentially means that the computing environment, including any applications running on it, have direct access to CPU and memory resources on the host server. Amazon EC2 service allows us to choose hardware resources from an extensive collection of pre-configured hardware options. We can choose a specific instance type and size, including the number of virtual CPUs or vCPUs, and the amount of RAM. And instance types are also configured with a specific level of networking throughput. Some types of instances also come furnished with other hardware resources, including high-performance resources like graphics cards and high-performance disks. It's a very wide-ranging collection of instance types and sizes to address virtually any workload requirement, from a T2 nano instance type with a fraction of a vCPU and a half gigabyte of RAM to instance types with 128 virtual CPUs or vCPUs and terabytes of RAM. Instance types are also categorized into instance families based on their capabilities and characteristics, like the ratio of vCPU to RAM or the types of storage options. So we have general purpose EC2 instance types, and this is a balanced mixture of CPU, RAM, and other resources. Then we have compute optimized, which include a relatively high amount of CPU power. We have memory optimized, which is an instance type with a relatively high amount of RAM. Then we have storage optimized instances, which include a relatively large amount of storage and throughput. Then we have accelerated computing, which includes dedicated graphics processing units or GPUs, or field programmable gate array resources such as 3D rendering and deep learning. Now, when choosing an instance, we select sizing attributes based on the current workload. And keep in mind that since EC2 instances are resizable, we can change the hardware allocation by stopping the instance, modifying the instance type attribute, and then starting the instance. EC2 instances require storage volumes for the root volume plus any additional storage. Let's consider the types of storage. In essence, persistent versus temporary storage. Persistent storage for EC2 instances can be configured using Amazon Block Store or EBS. An EBS volume is similar to a hard drive in that block storage volumes offer read-write access at a block level, and they may also be formatted with a file system. EBS volumes can be attached to specific instance, and EBS volumes are also ideal for installing operating systems and applications and for persisting data. EBS volumes can also be encrypted. Now, a couple of other interesting things to note about EBS volumes include the fact that they are decoupled from the physical host machine. What this means is that they can be detached from one instance and then reattached to another instance in the same availability zone. The physical host machine reads and writes to EBS volumes over the network, and accordingly, we can choose EBS optimized instances that actually reserve dedicated network bandwidth for EBS volume traffic. You can also take snapshots of EBS volumes, and the data associated with a snapshot is replicated across multiple availability zones automatically. Temporary storage is used by some EC2 instance types, which essentially means mounting instance store volumes locally on the physical host running the instance. Instance store volumes are excellent for high-performance storage for caching or temporary file storage, or for any use case where our application is already replicating the data. Now, since it's physically attached to the host machine, read-write performance is relatively high. But since this type of storage is local to the physical host, data persists only while the instance runs on the host. Data persists across reboots, but the data is deleted by AWS when the instance is stopped or terminated. An Amazon Machine Image, or AMI, is a template for the operating system and applications on the root volume of an instance, and you can allocate additional volumes when an instance launches. There are several different types of AMIs provided by AWS, including paid AMIs at the AWS Marketplace, and you can also create your own AMIs. Network interfaces for EC2 instances are virtual network interfaces known as elastic network interfaces. Now, these are linked to a software-defined network on Amazon Virtual Private Cloud, or VPC. Each instance is assigned a primary network interface linked to a subnet within an Amazon VPC. If not configured explicitly, EC2 instances get assigned to one of the subnets within the default VPC. An instance is assigned a private IP address for the communication with instances inside the VPC and a public IP address for communicating over the internet. Security groups are used to protect incoming and outgoing traffic over the network interface, behaving like a stateful firewall. In order to make a network connection to an instance, the security group rules must be designed to allow the connection. You can also attach additional network interfaces to an EC2 instance, each with its own MAC address and IP address associations. One thing to realize here is that the sheer number of network interfaces attached to an instance has no effect on network throughput of the instance. Throughput and bandwidth associated with an instance depend on the instance type and size. Linux-based EC2 instances by default provide remote access through Secure Shell, or SSH, while Windows-based EC2 instances use Remote Desktop Protocol by default. A default user with admin privileges is provided for initial sign-in. In order to obtain the credentials required to sign in as default user, an Amazon EC2 key pair must be specified when launching the instance. Now, the default user for Amazon Linux instances is EC2-user. Other Linux distributions may have a different default user. For example, the Ubuntu Linux default user is Ubuntu. For Windows instances, the default user is administrator. Named EC2 key pairs are composed of a public key and a private key. And we must realize that AWS retains the public key and we are responsible for securely storing the private key. If an EC2 key pair is specified when launching an instance, the provisioning process includes obtaining sign-in credentials. There are three primary states to an EC2 instance: running, stopped, and terminated, as well as intermediate states, including pending, shutting down, and stopping. When an instance is launched, it enters a pending state until it enters the running state. Once the instance is running, if it has EBS storage, the instance can also be stopped. When stopping, it enters the stopping state, and any data on instance store drives on the host are erased. Usually, each time an instance is started, it is launched on a different physical host. So if there is a problem with the physical host machine, stopping and starting the instance moves it to a different, presumably healthy host. Instances can also be terminated. When doing so, first, the instance enters a shutting down state. Then eventually, the instance is finally terminated. By default, EBS volumes associated with an instance are deleted when terminated. With respect to charges, an EC2 instance will accumulate charges for compute resources only when in the running state. But the thing is, EBS volumes persist data even while an instance is stopped, which means that there could be an associated charge. So this is just something to be aware of. Now, we can connect to EC2 instances and install any applications or software within an interactive session. However, to automate things, instead of logging into the instance, we can customize the software on the instance by providing user data when configuring an image at launch. By default, user data executes only at the first boot of the instance. Now, Instance Metadata Service, or IMDS, enables code running on an EC2 instance to discover properties about the instance. The Instance Metadata Service is associated with a special IP address, which is 169.254.169.254, which we can reference and query using HTTP to obtain a wide range of metadata attributes, including the instance ID itself, the credentials resulting from an IAM role, and it's even possible to retrieve the user data that was specified during launch to bootstrap the instance. In this video, we'll explore Amazon Virtual Private Cloud. The AWS Certified Developer Associate exam may test our knowledge of Amazon VPCs by posing questions that involve network troubleshooting, so it's wise to be very familiar with Amazon VPC. Amazon VPC comprises logically isolated networks within an AWS account. Networks are software-defined and can span all availability zones within a particular AWS region. We maintain complete control, though, over the connectivity of a VPC, including whether it's connected to other VPCs, to the internet, or to a private on-prem network. We define a VPC with blocks of addresses specified in classless interdomain routing, also known as CIDR notation. By default, VPCs are isolated, so instances within a VPC can't communicate with other networks, including the internet, until we explicitly create connections. The types of connections that we can make between VPCs and other networks includes an egress-only internet gateway, which is a special type of internet gateway for IPv6 that allows outbound traffic and related responses but blocks inbound connections. Amazon VPC endpoints allow traffic from a VPC to be directed to a specific AWS service or third-party software as a service, without traversing across an internet gateway. The AWS Transit Gateway allows us to centrally manage connectivity between multiple VPCs and an on-prem environment with a single gateway. Amazon VPC peering establishes a peer relationship between VPCs so that traffic may be privately routed from one VPC to another. And Virtual Private Gateway allows us to establish private connection to a corporate network using a VPN connection or a Direct Connect DX connection. And Internet Gateway is a highly available connection allowing outbound and inbound requests to and from the internet. Now, with respect to VPC IP addresses, private IP addresses are IPv4 addresses not reachable from the internet. These addresses are used for traffic to be routed privately, like internal within a VPC. This allows for private communication with other VPCs or for private communication with corporate networks. Public IP addresses can be assigned to an EC2 instance if so configured when launching the instance, and of course, the public IP address is an IPv4 address that is reachable from the internet. AWS automatically allocates and manages the association between an instance and its public IPv4 address, and the association only persists while the instance is running. In other words, we cannot manually manage the association of public IP addresses with an instance. Now, one caveat to that is an elastic IP address. This is an IPv4 address reachable from the internet, but unlike public IP addresses, we can manage the association between instances and elastic IP addresses. We can draw addresses from a pool of IP addresses managed by AWS or from IPv4 addresses we can bring into our AWS account. We can associate an Amazon-provided block of IPv6 addresses to a VPC. When enabling IPv6 in a VPC, IPv4 and IPv6 communications take place separately. In other words, operating in dual stack mode. In this way, resources can communicate over either protocol or both protocols. VPCs have subnets. So we define one or more subnets within a VPC. A subnet is linked to an availability zone within the region where the VPC is deployed. Each subnet is allocated its own block of private IP addresses that are defined using classless interdomain routing or CIDR notation. The block of addresses describes a subset of the IP address range assigned to the VPC, and it does not overlap with any other subnet in the same VPC. When launching an EC2 instance into a subnet, the primary network interface is assigned a private IPv4 address automatically from the subnet's CIDR range. In most cases, we create at least two types of subnet configurations. One that we launch instances into that we want to be able to reach directly from the internet, like an instance running a web server, for example, and this is known as a public subnet. The other typical subnet configuration is a subnet for back-end instances that are accessible from other instances, but not directly accessible from the internet. These are known as private subnets. So we would launch the web server into the public subnet, and we could launch an instance running a database that the web server must be able to access into the private subnet. Vpc Routing Tables. Routes defined in a route table control the network traffic exiting a subnet. These routes determine how the implicit router in the VPC routes outbound IP traffic from a subnet to a destination external to the subnet. Each route table has a specific rule called local route. This is the rule that allows traffic from an instance in one subnet within the VPC to send traffic to other instances in any other subnets defined within the same VPC. A route is comprised of two components, a destination and a target. Now keep in mind that when launching an EC2 instance into a public subnet, you must assign a public IP address to the instance because without one, the instance will not be able to communicate across the internet. A security group essentially acts as a stateful firewall for EC2 instances. When defining security group rules, we indicate the source or destination plus any protocols and ports that we want to allow. Inbound security group rules allow us to control the source, protocols, and ports for inbound traffic. For example, when we configure connection information for an instance, say for example a Linux instance, we specify an incoming rule to allow SSH traffic over port 22. Outbound rules allow us to control the destination, protocols, and ports for outbound traffic. A default outbound rule is assigned to security groups, allowing all outbound requests over all protocols and ports to all destinations. We can tighten the outbound traffic rules up by removing the default rule and adding our own outbound rules instead. Network access control lists, which I'll call network ACLs, allow an administrator to manage and control traffic entering or leaving a subnet. A network ACL consists of inbound and outbound rules that may be linked to multiple subnets within a specific VPC. A network ACL essentially acts as a stateless firewall against traffic inbound to or outbound from a specific subnet. Security group rules provide us with the capability to allow traffic, while network ACL rules are capable of allowing specific types of traffic and to deny specific traffic. But again, since network ACLs are stateless, they don't track connections and their replies. What this implies is that in order to allow a particular type of traffic over the network ACL, both inbound and outbound rules must allow it on the network ACL. If a network ACL is not specified for a subnet, then it gets associated with the default network ACL for the VPC, which has rules allowing all inbound and outbound traffic. In this video, we'll explore the AWS Shared Responsibility Security Model. Basically, under the AWS Shared Responsibility Security Model, security and compliance is a shared responsibility between AWS and the customer. AWS is responsible for the security of the cloud, which entails securing physical access to infrastructure. This infrastructure is located in AWS regions and availability zones. And this means that AWS is responsible for restricting access to servers and physical networks. Let's compare responsibilities of both customer and AWS side by side. As an AWS customer, we are responsible for security on the cloud. This means making secure choices when configuring our infrastructure, including data. For example, taking advantage of AWS encryption options. We're responsible for platform, application, and access, including the creation of suitable firewall rules. We're also responsible for the guest OS, for networking, and for firewall configuration. As mentioned, we can take advantage of AWS encryption options to encrypt data, both client-side, server-side, and also in transit. We are also responsible for controlling our own network traffic. AWS is responsible for the security and maintenance of the core software for all the provided services, including compute, storage, database, and network services. For the AWS hardware infrastructure, including regions and availability zones, as well as edge locations. Now let's consider an example. Consider the Amazon EC2 service. AWS is responsible for the underlying core software on the physical host machines, including the maintenance of the virtualization layer. Our responsibilities include ensuring that sensitive data is secured. We're also responsible for ensuring that the guest operating system, that's the guest operating system, is patched on a regular basis. And actually, AWS provides a lot of tools that can automate many of our responsibilities. For example, using AWS Systems Manager to automate the patching of EC2 instances. Nevertheless, we are still responsible for patching on a regular basis. It's just that we can automate that through AWS System Manager. We're also responsible for managing the guest operating system's user accounts and for securing any applications installed on the instance. Many AWS services are offered as managed services. And in the context of our discussion, this has a major impact. When using managed services, we typically see that our responsibilities have been streamlined. Take Amazon RDS, for example. In this case, AWS manages the software installed on the core database instance, and we only interact with the database using a specific SQL client rather than a database shell session. Furthermore, we don't install our own software on the database instance. Instead, AWS manages the operating system and software on the database instance. With unmanaged services, we have more control over low-level customizations and configurations, but with that additional control comes more of the shared responsibility. In this video, we'll work with Ec2 Instances. We'll select and launch an Amazon Ec2 instance. I've opened my browser and I've logged into AWS Management Console with my Iam User. I've got a second tab open, and on that second tab, I've navigated to aws.amazon.com/about-infrastructure/regional-product-services. I'm on the Regional Table tab, and this page clearly shows that in the Americas, the Northern Virginia region provides the vast majority of services offered on AWS. It also offers 6 availability zones to Ohio's 3. And I can see that if I click on Regions and AZs and scroll down and find the availability zones for each. So that's 6 for Northern Virginia, 3 for Ohio. I'm going to choose Northern Virginia to deploy resources in. I'll click the AWS Management Console tab to return to the AWS Management Console. I'll click the down arrow on the address bar beside the Ohio region that I'm currently working in. And this region was allotted to me when I created this AWS account. In the list of regions that appears, I'll choose US East, Northern Virginia, and now all the resources that I deploy will be deployed in US East, Northern Virginia. Now on the menu bar, I'll click the down arrow to expand services, and under Compute, I'll click EC2 to go to the Ec2 Management Console. On the Ec2 Management Console, I'll close the notification welcoming me to the new Ec2 console. And now under Resources, I have no running instances. To launch an instance, I can scroll down and select Launch Instance, or I can select Instances under the Instances heading in the navigation menu on the left. So I'll click Instances, and now I'll click Launch Instance, and now I can choose my Amazon machine image. I have a number of Amazon machine images that I can choose from. Some are eligible for the free tier, some are not. But if I scroll down, I can see several different types of images. Now I'll scroll back up and I'll click on Free Tier Only to filter only the free tier eligible images. And I see several, including different distributions of Linux and even some Windows machines. So these are eligible for the free tier. I'll scroll back up and I'll just select the Amazon Linux 2 machine image. This Amazon Linux 2 machine image is not only free tier eligible, but it also comes with everything that we need for this demo. So I'll click Select. Then I'll choose an instance type, and for this I'll choose the free tier eligible T2 Micro, which is by default selected. Now, at this stage, I could just go to Next Configure Instance Details and step through the different configuration stages, but I'm just going to click Review and Launch and accept all of the defaults for this machine image. So I'll click Review and Launch. That brings me to the Review Instance Launch page. And now I'll click Launch. And now before I launch the instance, I have to define new key pair. And in the Select an Existing Key Pair or Create a New Key Pair dialog, I'll click the down arrow beside Choose an Existing Pair, and I'll select Create a New Key Pair. And I'll give the new key pair a relevant name. I'll call it EC2-Linux-1. I'll click Download Key Pair. Now this is a requirement. I have to download in order to continue. I have to download this private key file because we use that when we want to access this EC2 instance. So if we wanted to remote into this EC2 instance, we would need that private key file. So in the opening EC2-Linux-1 dialog that appears, ensure that Save File is selected and click OK. And now I can click Launch Instances. And this opens a Launch Status page. Scrolling down, I'll click View Instances. On the Instances page, the instance state is pending. So we give it a few seconds, and the instance state turns to running. If I scroll down, under the Description tab are all the relevant details about this machine. Now, if I want to interact with the machine, say I want to stop it, make sure that machine is selected, click the down arrow beside Actions to open the Actions menu, point to Instance State, and we have several options. We have Stop, Reboot, Terminate. So let's click Stop. Now the Stop Instances dialog appears. I'm sure I want to stop this machine, so I'll click Yes, Stop. And now the machine is stopping. So now if I go to the navigation menu and click EC2 Dashboard, I'll see that I now have 0 running instances because I just stopped it. Okay then, so we've successfully selected and launched an Amazon EC2 instance. In this demo, we'll connect to EC2 instances using Secure Shell. Okay, I've logged into AWS Management Console in my browser as my Iam administrative user. In the menu bar, I'll expand Services, and under Compute, I'll click EC2 to navigate to the Ec2 Management Console. Now, I currently have one running instance. So I'll click on Running Instances, and this brings me to the Instances page, and I have one running instance, and that is an Amazon Linux 2 image. So I can Secure Shell or SSH into this image. To connect, ensure that the instance is selected, and then click Connect. In the Connect to Your Instance dialog that appears, we have 3 options. We can use a standalone SSH client, we can use Session Manager, or we can use EC2 Instance Connect, which is a browser-based SSH connection. To access our instance using a standalone SSH client, we're not going to use PuTTY, which is one of the options listed here. But you should be aware of step number 3 here. What happens is that you have to make the key not publicly viewable in order for SSH to work. And to do that, you use the chmod command specifying 400 against ec2-linux-1.pem. In the example, I'm going to highlight this SSH command and right-click and select Copy. And now go to PowerShell by clicking the PowerShell icon on the taskbar. And I'm going to PowerShell because post-August 2018, Windows 10 and Windows Server 2019 included OpenSSH. So we'll just ensure that this machine has SSH installed on it. So I'll maximize PowerShell. I'll CD into Downloads where my private key is located. I'll clear the screen by typing CLS and pressing Enter. And now I'll paste that SSH command in. This SSH command uses the -i flag for identity file. So we specify our identity file or the PEM file here. and then Ec2-user, which is the user on the Amazon Linux 2 machine image, the @ symbol followed by the public DNS, and I'll press enter. Now I'll type yes to are you sure you want to continue connecting, and I am now connected by secure shell to this machine. So I'll just type ps aux to see the running processes, and then I'll type exit to exit out of this machine. Now back on the local machine, I'll type CLS and press enter to clear the screen. Okay, now I'll close PowerShell. And this reveals the connect to your instance dialog which appeared earlier. Now I'm going to select Ec2 Instance Connect to use this method to connect to the machine. I won't be using Session Manager in this demo. Choosing the Ec2 Instance Connect option, the username is Ec2-user, so I'll click Connect, and this opens a connection in a new browser window. Okay, and I am connected to this Amazon Linux 2 machine image. I'll maximize this window, and I'll type PSAUX to see the running processes on this machine. Then I'll type exit to exit out of this machine. And so we've successfully SSH'd into the machine using a standalone SSH client and using the Ec2 Instance Connect method. In this demo, we'll connect to an Ec2 instance using Remote Desktop Protocol. In my browser, I've signed into Aws Management Console as my Iam administrative user. On the menu bar, I'll click the down arrow beside Services and click EC2 under Compute to go to the Ec2 Management Console. In the left navigation menu, I'll click Instances, and I'm going to click Launch Instance. And this time, I'm going to select a Windows-based instance, but I'm going to keep it on the free tier. So I'll click the checkbox beside free tier only, and now I'll scroll down and select the first Windows Server 2019 base image that I see. So I'll click Select. Now I'll leave the default T2 Micro instance type selected. It's the only one that's eligible for the free tier. Now, if I wanted to configure some of the instance details, I could just click Next, Configure Instance Details. There's nothing here that I want to change, but it's good to understand the options that are available here. And we'll see a lot more of this later in the course. So now I'll click Review and Launch. Okay, on the Review Instance Launch page, everything looks good. So I'll scroll down and I will click Launch. And now the Select an Existing Key Pair or Create a New Key Pair dialog appears. And we have to download our private key here. I'll click the list box where it indicates Choose an Existing Key Pair, and in the options that appear, I'll choose Create a New Key Pair. I'll give the new key pair a relevant name like EC2-Windows-1, and I'll click Download Key Pair. Ensure that in the opening dialog that appears that Save File is selected and click OK, and I'll click Launch Instances. Now on the Launch Status page, I'll scroll down and click View Instances, and my Windows Server 2019 instance is starting. So while I'm in here, just to ensure that we can distinguish between the two machines, I'm going to click the pencil icon beside my instance that's starting up. That's my Windows Server 2019 instance. And I'll give it a name of Windows Server 2019. And while I'm at it, I'll give the Linux image the name Linux. So now I can distinguish between these two machines quite readily. And now it shows the instance state for my Windows server as running. So let's unselect the Linux machine. We'll leave the Windows Server 2019 machine selected, and we'll click Connect. This opens the Connect to your instance dialog. We have two connection options here. We have a standalone RDP client and Session Manager. We're just going to use a standalone RDP client for this demo. Okay, so I'll click Download Remote Desktop File. And the thing is, with Windows images, we're going to use the key in order to reveal the password. So if I carry on here in the opening dialog as I am, I'll leave open with selected, and the default application is remote desktop connection, and then I'll click OK. Now this opens the remote desktop connection. If I click connect, the Windows security dialog appears, and I'll see that I need a password. Well, I don't have a password, so that's what I have to go and reveal. So in the Windows security dialog, I'll click cancel. Back on the connect to your instance dialog, I'll click get password. Now the connect to your instance get password dialog appears. So I'll click browse to find the key pair that was associated with this instance when it was created. And in file upload dialog, I'll navigate to downloads, and I'll select the ec2-windows-1.pem file, and I'll click open. And now I click decrypt password, and that reveals the password for this machine. So I'll copy the password to the clipboard by clicking the copy icon, and I'll click close. Now I can click connect again. That opens the connect to your instance dialog. I'll click download remote desktop file. In the opening dialog, I'll click OK. In the remote desktop connection dialog, I'll click connect. In the Windows security dialog, in the password field, I'll paste my password. I'll click the checkbox beside remember me, and then I'll click OK. Now in the remote desktop connection dialog, click yes. Okay, and now I'm connected. And so I've successfully connected to a Windows Server 2019 Amazon machine image with remote desktop protocol. In this demo, we'll create and configure an Amazon Virtual Private Cloud, or VPC. AWS creates a default VPC for us, but when we need to go outside the default VPC, we have full power to do that. To get started, I've logged in as my admin Iam User, and I've navigated to the Ec2 Management Console. I'm here because first I'm going to create a key pair to associate with my new VPC. To do that, in the left navigation menu, scroll down and under Network and Security, click Key Pairs. Click Create Key Pair. Now I'll give the key pair a name. I'll call it EC2-key pair. For file format, I'll choose PEM. That's for use with OpenSSH. PPK is useful for PuTTY, but we're going to use OpenSSH. So I'll click Create Key Pair, and then I'll click OK in the opening dialog that appears, and now I have my new key pair. All right, now let's go to Services and type VPC and click VPC from the list of matches, and I'll click Launch Vpc Wizard. All right, and in step 1, I select a VPC configuration. I can select a VPC with a single public subnet, a VPC with public and private subnets, a VPC with public and private subnets and hardware VPN access, and a VPC with a private subnet only and hardware VPN access. For this demo, we're just going to create a VPC with a single public subnet. Now this is going to create a /16 network and a /24 subnet. So now click Select. And now in step 2, we'll leave the CIDR block as is with a /16 network. And for the VPC name, I'm just going to call this my-VPC. In the public subnets IPv4 CIDR, we've got a /24 network. We'll leave that as is. We'll leave the subnet name as is as well. If we wanted to configure service endpoints, here we just click Add Endpoint, and then we can select an endpoint to add. I'm going to close because we're not going to add an endpoint in this demo. For hardware tenancy, I'll leave the default. I could also choose dedicated. And now I'll click Create VPC. And now AWS creates all the resources that are required by my VPC, including subnets, security groups, network ACLs, gateways, route tables, and so on. All right, so we've successfully created a key pair and a VPC that we can use to deploy our EC2 instances into. In this demo, we'll configure security groups. And we want to be able to work with security groups in order to manage the security of our EC2 resources. We can use security groups in the context of our EC2 instances in order to allow inbound and outbound ports and IPs. To get started, navigate to the Ec2 Management Console. So I'm at Aws Management Console. I'm going to expand Recently Visited Services, click EC2, and then in the left navigation menu, scroll down, and under Network and Security, I'll click Security Groups. Now, I already have a couple of security groups. The security group called Launch-Wizard-2 is for RDP into my Windows servers. So if I expand the bottom part, I can see the inbound rules, RDP, TCP protocol, port range is 3389, and the source is anywhere. Okay, so let's click Create Security Group to create our security group. Now, this security group is going to be for my web servers, and these are Linux machines. So first of all, under Basic Details, I'll give it a relevant name. How about Web Server-Group? And then for description, I'll specify Allow SSH access to web servers. And for the VPC, I'll click the down arrow, and I've got a couple of VPCs, one that I created on my own. I'll select the one that I created on my own. And then scrolling down, I'm going to add my inbound rules. Now, if I look at my outbound rules, so scrolling down a little bit further, so my outbound rules allow all traffic going out from these machines. So that's fine. I'll click Add Rule in my inbound rules. And for type, I'll click the down arrow to expand the drop-down list, scroll down, click SSH, and I see the protocol and port range have been populated. For source, I'll click the down arrow to expand the drop-down list, and I'll select my IP. So that allows only my IP access over port 22 into my web servers. For description, which is optional, allow only my IP access over port 22. Now click Create Security Group, and done. Okay, so we've effectively created a security group that we can now use to deploy our EC2 instances into and ensure that only our IP address has access to those web servers over port 22. In this demo, we'll configure instance details, including number of instances, network, storage, tags, and so on. Okay, I've signed into AWS, and I've navigated to the Ec2 Management Console, and I'm on my Ec2 dashboard. I have 0 running instances, and I'm going to create an instance. So I'm going to click Running Instances, and I'll click Launch Instance. On the Choose an Amazon Machine Image, AMI Step 1, I'll choose the Amazon Linux 2 machine image. So I'll click Select beside this image. Now for the instance type, I'm going to leave the free tier eligible T2 micro selected, and I'll click Next, Configure Instance Details. So there are a lot of configuration options here that we can configure. To start with, we have the number of instances. Now I can choose to launch multiple instances of the same machine image, and not only that, I can deploy those images into an auto-scaling group and configure policies to automatically scale the number of instances in the group. We'll deploy one now. We'll work with auto-scaling groups in some detail later in this path. Then for purchasing options, if we check Request Spot Instances, we see a number of other parameters appear. For example, the current price, the maximum price that we're willing to pay. We can check the Persistent Request checkbox to ensure that our request for spot instances will be submitted every time our spot instance is terminated. And we also have a period of time that we can make that request valid from and to. We'll uncheck the Request Spot Instances checkbox because we want an on-demand instance. For network, we can choose the default VPC, or if we click to expand the drop-down, I'll choose my own VPC that I've created. We'll leave the subnet at its default settings. Now, auto-assign public IP right now is disabled. Click to expand the drop-down and select Enable. Now we can choose to launch an instance into a placement group for redundancy or network throughput demands if we want to, but we'll leave this unchecked for now. We don't need any IAM roles for this particular instance. And for shutdown behavior, we'll leave the default at stop, and the rest of the settings in this section are fine as they are. T2/T3 Unlimited refers to the fact that T2, T3, and T3A instances are also eligible for burstable performance. They're designed for a baseline level of CPU performance, but they carry with them the capability to burst to higher levels as required by the workload. This setting is fine as is. We'll leave it unchecked. We can also create a new elastic file system, but we won't do that at this time. We've also got network interfaces. We can add network interfaces at any time. And under advanced details, right now, metadata is accessible, and we'll leave that enabled. And then we have user data, and we're not going to touch that at the moment, but we'll see that again later in the course. Okay, click Next, Add Storage. When starting an instance, we need a root volume because this is where the operating system is stored. EBS volumes are reliable, high availability storage volumes that can be attached to any running instance that is in the same availability zone. In our case, we've got an EBS volume as our root volume. Its size is 8 gigabytes. It's a general purpose SSD volume type. We've got delete on termination checked. We'll leave that checked. And we see that it's not encrypted. We can choose to encrypt it, but we'll leave it not encrypted at this time. Click Next to add tags. And I'll add a tag. That tag is name. And for this instance, I will call this Web Server 1. Click Next, Configure Security Group. And now we can create a new security group or select an existing one. I'll click to select an existing security group. I've got a web server group that allows SSH access to web servers. So I'll click to check that one. And now I'll click Review and Launch. And now reviewing the settings, now that we're happy with them, let's click Launch. And now for the key pair, we can either choose an existing key pair or we can create a new one. I've got one already that I created for the purposes of launching EC2 instances and attaching to them. So I'm going to click I acknowledge that I have access to the selected private key, and I'll click Launch Instances. Okay, on the Launch Status page, scroll down. On the bottom right side, click View Instances. And the new instance that we just created, Web Server 1, is currently starting. So instance state reports as pending. And now instance state reports as running. Now let's click on it and let's click Connect. Now we'll use the standalone SSH client. So I'm going to highlight the example SSH command. Right-click, select Copy. Down to the taskbar, I'll start PowerShell. I will CD into Downloads. That's where my key file is located, my private key. Let's clear the screen by typing CLS and pressing Enter. And let's maximize PowerShell window. Now I'll right-click to paste that command in, and let's press Enter. I'll type Yes to indicate that I want to continue connecting. Press Enter. And now I'm connected to my Amazon Linux 2 machine image. Okay, so we've successfully configured instance details, including the number of instances, the network, storage, tags, and so on. In this demo, we will allocate, associate, disassociate, and release elastic IPs. To use an elastic IP, you first have to allocate one to your account, then associate it with an instance or a network interface. A disassociated elastic IP address remains allocated to your account, that is, until you release it explicitly. Plus, when you associate an elastic IP address with an instance that previously had a public IP4 address, the public DNS hostname of the instance also changes to match the elastic IP address. This is useful for when you need a static IP address. I've signed into Aws Management Console and I've navigated to the EC2 dashboard. I'll click Running Instances. I have one running instance at the moment. I'll click on it, and on the Description tab in the bottom pane, I have a public DNS and a public IP. If I want to connect to this machine, say for example through Secure Shell, SSH, I can do that. I've set up my VPC, I've got my security set up so that I can actually do that. However, what happens if I try to use that same IP and public DNS to connect again once I stop and restart this machine? Well, it won't work. And it won't work because when you stop and start an instance, the IPv4 public IP goes away. And when it starts up, it gets a new one. So for example, let's stop Web Server 1. Web Server 1 has been selected. I'll click Actions, point to Instance State, select Stop, and in Stop Instances dialog, I'll click Yes, Stop. Okay, so now the machine is stopped, and I'll note that the public DNS and the public IP have both gone away. Now let's point to Actions again, select Instance State, and select Start. In the Start Instances dialog, click Yes, Start. Okay, now that the machine has started, note the very different IPv4 public IP and public DNS. Now let's create an elastic IP. So over in the left navigation menu, I'll scroll down, and under Network and Security, I'll click Elastic IPs. Now I'll click Allocate Elastic IP Address. And the only choice I have is Amazon's pool of IPv4 addresses. I haven't provided a pool on my own with this account. So I'll click Allocate. And now I have a public IPv4 address. Incidentally, I can assign tags to this address. Let's expand the bottom frame and click Tags. Click Manage Tags. And for my first tag, for key, I'll specify name. And for value, I'll specify static IP. I'll add another tag by clicking Add Tag. This time I'll specify owner, and the owner of the tag, we'll say this is operations. And click Save. Okay, so now I have an elastic IP. That elastic IP has been allocated to my account, but it hasn't been associated with an instance yet, or an interface. Let's go ahead and do that. With my new elastic IP selected, I'll click Actions to expand the drop-down list, and I'll scroll down and I'll select Associate Elastic IP Address. Now on the Associate Elastic IP Address page, for resource type, I'll choose Instance. It's the default selection, so I'll leave that selected. And now for instance, I'll choose an instance. So I'll click inside the box and I'll choose Web Server 1, which is the only one that I have running. Note, I can also associate the private IP address with an elastic IP address, but we're not going to do that now. I can also specify whether this elastic IP can be reassociated with different resources. I'm going to click Associate and leave everything else at its default setting. Okay, and the notification at the top of the window tells us that the elastic IP address has been associated. So now let's go back to the EC2 dashboard. I have one running instance. Let's click Running Instances. click to select web server 1 and note the new public IP address and new public DNS. Now, what happens if I stop this server? Well, let's try it. I'll click Actions, Instance State, click Stop, and in Stop Instances dialog, click Yes, Stop. Okay, and now note something very different. Now that this server is stopped, I still have a public IPv4 address and I have a public DNS. And this is because an elastic IP is a static IP address. So now if I restart this server, it will still have the same IP address that it did when I associated this particular elastic IP with this machine. Now, what happens if I disassociate and release this elastic IP? Well, let's check that out. In the left navigation menu, I'll click Elastic IPs. I've got one elastic IP. I'll expand the top part so we can see our IP. And now I'll expand Actions. And first, I'll disassociate the elastic IP address by selecting Disassociate Elastic IP Address. And in the Disassociate Elastic IP Address dialog, I'll click Disassociate. Okay, and now going back to the EC2 dashboard, clicking on Web Server 1, I see now that that public DNS and public IP have gone away. And that's because I disassociated that elastic IP from this machine. Now, we want to release that elastic IP. So let's go back to Elastic IPs in the left navigation menu. Make sure that the static IP has been selected. Expand Actions and select Release Elastic IP Addresses. And in the Release Elastic IP Addresses dialog, click Release. And done. So we no longer have any elastic IP addresses. So now if we go out to the EC2 dashboard, we'll see now that we have 0 elastic IPs. Okay, so we've successfully allocated, associated, disassociated, and released elastic IPs in this demo. In this demo, we'll install and update software on an EC2 instance. I've signed into my AWS account and I'm on my EC2 dashboard. I have one running instance, so I'll click Running Instances under Resources, and I'll click the checkbox to select the Web Server 1 instance, and then I'll click Connect. I'll grab the SSH connect command for this instance, so I'll highlight it, right-click, select Copy. Down in the taskbar, I'll click to Open PowerShell. Let's maximize the PowerShell window. And now CD into Downloads, that's where my private key is located. And I'll type CLS and press Enter to clear. Now, I'll right-click to paste that command in order to connect to my server, and I'll press Enter. Okay, so now I'm connected to my server. This is an Amazon Linux 2 machine image. And to clear the screen, I'll type Clear and press Enter. To get started, we have to ensure that all the software packages are up to date first. So we'll perform a software update on this instance. To do that, we'll use the yum update command. Now we'll have to use sudo in order to run this as a super user or root user. So that's sudo yum update -y. I use the -y in order to suppress the confirmations asking if I want to actually install these updates. If you want to see the updates before they're installed, just omit the -y. Okay, pressing Enter, and my system was already up to date. So now I'll clear again by typing clear and pressing Enter. Okay, now to install Apache. And to do that, I'll type sudo yum install -y httpd. Okay, and done. Now I'll type clear again and press Enter. At this point, now I can start the Apache service. To do that, I'll just type sudo systemctl start httpd. Typing clear again and pressing Enter. And now I want to use the systemctl command again to configure the Apache web server to start each time the system is booted. And to do that, I'll type sudo systemctl enable httpd. And now I can verify that httpd is running by using systemctl command again with is-enabled. So I'll just type sudo systemctl is-enabled httpd and press enter. And the system reports that indeed Apache or httpd service is enabled. So now I will clear one more time. Now at this point, if I were to go to my browser and open a new tab and go to the public DNS, let's see what happens. So we'll grab the public DNS for our server. So beside public DNS, I'll highlight it, right click and select copy. Alternatively, there is a copy icon beside it if you hover over the public DNS. All right, let's paste this in and see what happens. And nothing. It's not going to work because we need to add a security rule to allow inbound HTTP traffic over port 80. So let's kill this by closing the tab. And now let's pull the bottom part up a little bit so that we can see our security groups clearly. Okay, so here's the web server dash group. Let's click to open the web server group. There's our web server group now. I'll expand the bottom here again so that we can see the inbound rules. So that's it. We have one rule. It's for SSH only. So there's nothing allowing inbound traffic over port 80. So let's click Edit Inbound Rules. We'll click Add Rule. And under Type, we'll click the down arrow and we'll select the pre-configured HTTP rule. And for source, it's custom, and we'll specify the everything CIDR block. So that's 0.0.0.0/0. Click Save Rules, and done. Okay, so now let's go back and look at our instance again. Select Instances in the left navigation menu. And now we'll grab that public DNS by clicking the copy to clipboard icon. And now let's open a new tab, paste that in, and go. And now I see the Apache test page, so everything is working. So we've successfully installed Apache and updated all the packages on our EC2 instance. In this demo, we'll configure a web server's document root permissions. The Apache HTTP daemon, or HTTPD, serves files that are kept in a directory that's known as the Apache document root. The Amazon Linux 2 Apache document root is /var/www/html, and by default, this directory is owned by the root user. We need to allow the EC2 user account to manipulate files in this directory. And to do so, we need to modify the ownership and permissions of the directory. So in this demo, to accomplish that, we'll add the EC2 user to the Apache users group. And we'll also assign the Apache group ownership of the var www directory. We'll also assign write permissions to the group. To get started, I've signed into Aws Management Console and I've navigated to my EC2 dashboard. I have one running instance. That's my web server. So I'll click to open the running instances. I'll click the checkbox beside Web Server 1. That's our web server that we're going to be working with. And I'll click Connect. I'll grab the SSH Connect command. So I'll highlight it, right-click, select Copy. Now down on my taskbar, I've pinned the Windows PowerShell icon to the taskbar. So I'll click to open Windows PowerShell. I'll maximize the window. I'll CD into Downloads. That's where my private key is. I'll clear the screen by typing CLS and pressing Enter. And now I'll right-click to paste the Connect command into Windows PowerShell, and I'll press Enter. Okay, and now I'm connected. Now to clear the screen on an Amazon Linux 2 machine image, I'll just type clear and press Enter. All right, now the first part involves us adding the EC2 user to the Apache group. So I'll type sudo usermod -a capital G Apache $user. Okay, now to pick up the new group for this session, I'll use the new group command. So I'll type new grp Apache and press enter. Okay, now let's clear. Now to verify the membership in the Apache group, type groups, and it reports that indeed we have accomplished that first part. So the EC2 user is now a member of the Apache users group. So let's clear again. Now, we need to change the group ownership of var www and its contents to the Apache users group. And to do that, I'll type sudo chown -R ec2-user :Apache /var/www. Pressing enter. And now that that's done, we need to add group write permissions, and we'll set the group ID on future subdirectories and change the directory permissions of var www and its subdirectories. To do that, first I'll clear, and then I'll type sudo chmod 2775 /var/www $find /var/www -type D for directory -exec sudo chmod 2775 open curly brace close curly brace /; pressing enter and done. Now I'll clear, and now we need to add group write permissions in a recursive manner. So basically, this recursively changes the file permissions of var www and its subdirectories. And to do that, I type find /var/www -type F for file -exec sudo chmod 0664 open curly brace close curly brace /; pressing enter and done. Now the EC2 user, and in fact any future members of the Apache users group, can add, delete, and edit files in the Apache document root for our server. Let's look at the output. So first, let's add some output into index.html in the document root, because without that, we're just going to see the Apache test page. So I'll type echo, open quote, hello world, ellipsis, $, open parenthesis, users, close parentheses, on $, open parentheses, hostname -f, close parentheses, close quote, right angle brace /var /www /html /index.html. So this will add this command into index.html, and this will render the user and the hostname of the machine along with a hello world message when we go and navigate to the web page. So pressing enter and done. So now let's clear. And now let's just double check to make sure this is going to work. So I'll type wget -q O hyphen localhost. Now the -q suppresses wget's output, and -O means that the documents will not be written to the appropriate files, but will be concatenated together and written to a file. Now if the hyphen is specified, which is what we've done here, then the documents will be printed to standard output. Okay, so that means we're going to see the output here. So let's go ahead and press enter. And there's the output. Hello world, EC2 user, on, and the host name. So now let's go over to the browser. So down on the taskbar, I'll click the Firefox web browser icon. I'll close the Connect to Your Instance dialog. I'm going to grab the public DNS for our web server by clicking the Copy to Clipboard icon beside it. Now let's open a new tab, right-click, paste, and go. And we see the same message. So everything is working fantastic. So we successfully configured the web server's document root permissions to allow the EC2 user to manipulate files and directories in the document root. In this demo, we'll bootstrap EC2 instances by employing an EC2 user data script. When you launch an instance, you have the option of specifying user data to carry out automated configuration tasks or run scripts post-startup. When you bootstrap multiple instances at a time this way, for example, into an auto-scaling group, the user data is passed to all instances. I've signed into my AWS Management Console and navigated to the EC2 dashboard in my web browser. I also have my code editor open. I'm using Visual Studio Code. You don't have to use Visual Studio Code. I just find it to be a very convenient code editor. I also have Windows PowerShell open, and I've navigated into my downloads directory. That's where my private key is located. Okay, so back to the browser. Now, I've got 0 running instances. I'll click Running Instances, and I'm going to click Launch Instance. I'm going to select the Amazon Linux 2 machine image, so I'll click Select, and I'll use the T2 micro, so I'll click Next, Configure Instance Details. As I said, if we launch an instance using user data into an auto-scaling group, then each instance is passed the user data. So let's start 2 instances here. So in the number of instances field, I'll type 2. Now let's scroll down. And at the bottom is the user data field. Now we can specify the text. We can also specify a file. And we also have options using the AWS command line interface. We'll see that later in this path. You also have a checkbox to select if the input is already base64 encoded. Ours is not, so I'll leave that unchecked. So let's go back over to my code editor. In any script, and it's the same with our user data, we start the file with the familiar Linux shebang, in this case specifying that the script is going to be interpreted and run by the bash shell. That's line 1. Now from lines 5 through 8, we're updating the software packages and installing, starting, and enabling Apache. In line 11, we're adding the EC2 user to the Apache users group. And from lines 14 to 17, we're setting the folder and file permissions on the document root for the server and all the files under document root. And then on line 20, we're basically generating an index.html file so that we can splash some information to the home page when we navigate there using the public DNS. Okay, so let's highlight this code. I'll right-click, select Copy, back over to the browser, and I'll paste that into the user data field. Now next, we need to configure the security group. Everything else will leave at its default values. So click Configure Security Group. That's step 6. We've got an SSH rule already. We'll click Add Rule, and we'll expand the drop-down list. Find HTTP, and we'll leave that wide open. For SSH source, we'll expand the drop-down and select My IP. Okay, so now click Review and Launch, and everything looks good. So let's click Launch. And now select a key pair, the EC2-key pair that I generated earlier. Check the I acknowledge checkbox, and I'll click Launch Instances. All right, on the Launch Status page, I'll scroll down, and on the bottom right side, I'll click View Instances. And now we see that both instances are starting up. Okay, so both instances are up and running. So let's click Instance 1. We'll grab its public DNS. I'll click the Copy to Clipboard icon, open a new tab, right-click and select Paste and Go. And we see bootstrapped host at, and we have the public FQDN. And now let's go and grab the other machine. So I'll click to select the other instance. And now I'll grab its public DNS by clicking Copy to Clipboard, opening a new tab, and selecting Paste and go there. So this one is 172.31.42-123, and we also have 172.31.34-204. So both of these instances had the same user data. We just splashed a message that is dynamic in that it splashes the fully qualified domain name from the hostname command on Linux. Okay, so we've successfully configured EC2 instances with user data. So, in this course, we've examined the Amazon Elastic Compute Cloud EC2 web service, the Amazon Virtual Private Cloud Networks, VPC, Elastic Block Storage, EBS, and IP configuration. We did this by exploring how to work with the Amazon EC2 service and Amazon VPC networks, the AWS Shared Responsibility Security Model, how to select and launch an Amazon EC2 instance, how to connect to EC2 instances using Secure Shell and Remote Desktop Protocol, and how to create and attach EBS volumes to EC2 instances. We also explored how to use security groups to manage EC2 instance security, how to configure private, public, or elastic IPs as required, how to update and install Apache web server software on EC2 instances, and how to bootstrap EC2 instances using an EC2 user data script. In our next course, we'll move on to explore how to use the AWS Command Line Interface, or CLI, and AWS Software Development Kits, or SDKs, to interact with AWS and perform various tasks on the AWS cloud. In this video, we'll explore the various methods provided by AWS for interacting with AWS services and resources. Amazon Web Services provides various tools like the AWS Command Line Interface, or CLI, and various software development kits for interacting with AWS service APIs. To work with these various tools, they must be configured with specific information, including credentials information or other configuration details that are required in order to perform the requested operation. In addition, you should also be aware of an AWS CLI-like tool called AWS Tools for PowerShell, and it's designed specifically for PowerShell. The various tools offer multiple methods known as credential providers that we choose in order to supply the required credentials and configuration information for the requested operations. Now, although some credential providers are specific to the tool being used, there are some common credential providers that are shared by most tools. First, there are shared AWS configuration and credentials files. You can store configuration and credentials information in local files that the tools can access. There is a config file for storing configuration settings and a credentials file, which is a separate file for storing sensitive data like secret access keys. Each of these files stores groups of settings called profiles, and you can define multiple profiles and then invoke them when using the tools. Many configuration settings can also be stored in environment variables. There can only be one set of environment variables in effect, however, but they can be easily modified dynamically as required. There are also a number of configuration settings that can be specified when requesting a specific operation. These are known as per operation parameters. In this way, parameters may be changed as required based on the operation being invoked. When invoking an AWS tool or software development kit, they search for credentials or configuration settings in a specific order. Those tools stop looking once they've located values that they can use, so there is a precedence. Most AWS tools and software development kits check the credential providers in order by per operation parameter, environment variable, shared credentials files, and shared config files. But some tools and software development kits may check in a different order, while other tools like the AWS Software Development Kit for .NET may also provide other methods of storing and retrieving parameters. It's important to understand this precedence because if you're asked a question on the exam where there are different credentials in different locations, you'll have to know which setting is actually going to be used based on the order of precedence. The AWS Command Line Interface, or CLI, is a powerful tool that can be installed and configured to manage many AWS services from the command line. Further, they can be written into scripts to automate those operations. For example, the AWS CLI provides a collection of simple file commands for interacting with Amazon S3 services. The AWS CLI does not store any customer data other than the credentials required for interaction with target AWS services, and by default, all transmitted data from the client to the service endpoint is encrypted by sending everything through HTTPS TLS. Now, nothing is required to enable HTTPS/TLS, but you can explicitly disable it for an individual operation by specifying the no verify SSL flag. Essentially, the CLI allows us to implement much of the functionality and interact with various APIs using Linux or Mac terminals or shells, the Windows command line, or you can even use PowerShell as your command line. And all this interaction takes place remotely. Now, the AWS software development kits access API operations tailored to the language that is being used. And many languages are supported, including JavaScript, Python, PHP, .NET, Java, Ruby, and Node.js. Now, with respect to AWS APIs, there are RESTful APIs and there are WebSocket APIs. RESTful APIs are optimized to work with serverless workloads, while HTTP backends use HTTP APIs, and this is the appropriate choice for building APIs that just require API proxy functionality. API Gateway is the best choice if your API requires API proxy functionality and API management features. Now, WebSocket APIs allow us to build real-time, two-way communication applications like messaging or chat apps or streaming dashboards, for example. API Gateway maintains a persistent connection to handle the message transfer between backend services and clients. We'll explore API Gateway in some detail in a course later in this path. In this demo, we'll install the AWS Command Line Interface, or CLI, on a Windows development machine. I've opened my browser and navigated to aws.amazon.com/CLI. On this page are the various installers for the different operating systems. In this demo, we're interested in the installer for 64-bit Windows. A couple things to understand about the CLI. There are two versions of the CLI. Version 2 is the current version and is the recommended version for production environments. Version 1, while still available, has undergone some changes. Any builds of AWS CLI version 1 released after January 2020, and that starts with version 1.17, they require either Python 2.7 or Python 3.4 or later in order to use the CLI. So the interesting thing here is that the AWS CLI versions 1 and 2 use the same AWS command name. And if you have both versions installed, your system uses the first one it finds in your path. Consequently, Amazon recommends that to avoid conflicts, you uninstall client version 1 and use only CLI version 2. Okay, on the right side of the aws.amazon.com/CLI webpage, I'll click the 64-bit link to download the Windows installer. And when the opening dialog appears, click Save File. Now, while it's doing that, I'm going to go down to my taskbar and I'm going to open Windows Explorer. And this is where I have version 1 installed. It's under my users directory, under app data, roaming, Python, and my Python version, which is 3.7, and then under scripts. So now if I were to go to a terminal prompt, either through PowerShell or my command prompt, and type AWS in this directory, I would see the version of AWS client installed. I would see the version of Python that's used or associated with it, and I would also see the BODO or the AWS SDK for Python that's packaged with this version. Down on my taskbar, I've pinned the Windows PowerShell icon to my taskbar. I'll click to open Windows PowerShell. Okay, I'm going to CD into the directory where my CLI version 1 is located. I've copied that directory to the clipboard, so I'll just right-click here to paste it into Windows PowerShell. Once in this directory, I'll type /AWS-version. It reports that I have AWS CLI 1.18.49 installed. It's associated with Python 3.7.4, which is the version of Python that I have installed on the system, and the BODO Core SDK for Python. So let's clear this by typing clear and pressing enter. Now to uninstall this version, I'll just type pip uninstall AWS CLI and press enter. When asked to proceed, I'll press Y and press enter. And done. So now if I do a listing in this directory, I'll see only the Python scripts and executables that are available, not the AWS scripts and executables. Okay, so let's clear by typing clear and pressing enter. And actually, let's go over to the browser and click the download icon in the menu bar. I'll click to open the MSI file that was downloaded. And I'll click OK when asked if I want to open the executable file. And the AWS CLI installation wizard appears. On the welcome screen, click Next. Click to accept the license terms. Click Next. In custom setup, just click Next. And on the ready to install AWS command line interface v2 page, click Install. If you see a user account control dialog, click Yes, and the installation proceeds. All right, and it reports that it finished. So I'll click Finish to close the wizard. Down on the taskbar, I'll click the PowerShell icon to bring up Windows PowerShell. Now I'll close and reopen PowerShell to pick up the new path. So I'll maximize PowerShell. And now I'll type AWS-version. And this reports now that I have AWS CLI version 2.0.10 installed. It's bundled with Python 3.7.5. And it's got a newer version of the BODO Core Python SDK bundled with it as well. So we've successfully installed CLI version 2. And we can now use AWS CLI version 2 to interact with our AWS account. In this demo, we'll install the AWS CLI on an Ubuntu Linux 18.04 development machine. Before we get started, understand that AWS CLI versions 1 and 2 use the same AWS command name. If you have both versions installed, your system uses the first one it finds in your path. So Amazon recommends that you uninstall client version 1 and use client version 2. Now, if you have AWS CLI version 1 already installed, then you likely have pip already, but not necessarily. You may have installed AWS CLI version 1 from the bundled package. We'll get started by updating the apt cache by typing sudo apt update and pressing enter. All right, done. Now I'll clear. Now to install pip, because I have Python 3 on the Ubuntu 18 machine, it comes with Python 3. Type sudo apt-y install python 3-pip, and I'm using the -y flag just to suppress the confirmation. Okay, so pressing enter. Okay, and I was already up to date. So now to see what version of pip3 that you have installed, just type pip3 version, and I have pip 9.0.1. Okay, let's clear. If you do have AWS CLI version 1 installed, then just type pip3 uninstall AWS CLI. Now I don't have it installed, so that command won't work, but that's all you need to do. All right, so now let's install the curl utility, because we'll use that to grab the archived install for Linux from AmazonAWS.com. So to do that, I'll type sudo apt install -y curl and press enter. And done. Okay, so now we can use CRL to grab the archived install for Linux. So we'll do that by typing curl and in quotes https://aws-cli.amazon-aws.com/aws-cli-exe-linux-x86_64.zip and unquote and -o, and we'll output it to a shorter name, aws-cli-v2.zip. Okay, so let's go ahead and press enter. And done. So let's clear. Now I'll use the unzip utility on Ubuntu 18 to unzip the AWS CLI v2 archive. So I'll type unzip aws-cli v2.zip. And notice I don't need the sudo because I'm accessing my directory that I own. Okay, so pressing enter, and it's all extracted. So let's clear. So now if I do a listing, I'll see that I now have an AWS subdirectory under my home directory. And that's where the unzip utility extracted everything in AWS CLI v2. Okay, so let's clear. And now we can install AWS CLI. And we do that by typing sudo //aws because we're accessing the subdirectory under my home directory, AWS. And there's a file named install that has all the commands in it that will install the AWS CLI. So let's go ahead and press enter. Okay, done. Now let's type clear, press enter, and type AWS --version. And it shows that we have AWS CLI version 2 installed with Python 3.7. And it's got the Boto Core, which is the software development kit for Python, automatically installed with it. So we've successfully installed AWS CLI version 2 on an Ubuntu Linux 18.04 development machine. In this demo, we'll install the AWS CLI on Mac OS. Okay, I've signed into my MacBook Pro. I'm going to open a terminal prompt. Down in my dock, I'll click the terminal icon, and I'll maximize this window, and I'll clear. And now to get started, we'll use the curl utility to download the package file to install the AWS CLI version 2. And to do that, I'll type curl and in quotes https://aws-cli.amazon-aws.com/aws-cli-v2.pkg and make note of the uppercase AWS CLI v2 -o, and we'll call this AWS CLI v2 .pkg. Okay, so pressing enter. The package file is downloaded. We can now install. So first I'll clear. So I'll type sudo installer -pkg /awscliv2.pkg -target /. Okay, we used the -pkg parameter and we specify the path to the package file that we're installing. And then with the target parameter, we're specifying the volume mount point, which in this case is just /. Now the files are actually installed to user local aws-cli. And then the installer creates a symlink in user local bin. We need to use sudo because we need to have the right permissions in order to write to those folders, which I don't own as the user. Okay, pressing enter. Now I enter my password, press enter again, and the installer reports that the install was successful. So let's clear. We'll type AWS --version. And there we have AWS CLI version 2 with Python 3.7 and BottoCore, the Python SDK, also automatically installed with the bundle. So we successfully installed AWS CLI v2 on a Mac OS X machine. In this demo, we'll configure the AWS CLI so that we can securely interact with our AWS account using the CLI. The easiest way to configure access to the AWS account with the AWS CLI is to use the AWS Configure command. To get started, I've opened Windows PowerShell and maximized the PowerShell window. I've also got my web browser open. I'm signed in with my admin user, and I'm going to go and visit the Ec2 and the Iam consoles. But first, let's go back to PowerShell. And now if I specify AWS Configure by typing AWS Configure, I'll be prompted for 4 settings. The first setting is the AWS Access Key ID. The second setting will ask us for the secret access key. These are the credentials. So let's go back to the browser. We'll click Iam to go to the Iam dashboard. I'll click Users. I'll click on the username for my admin user. And now I'll click the Security Credentials tab. Scrolling down under Access Keys, I'll see that I have 2 active access keys. Now, here's the problem. The only time that you can view or download the secret access key itself, not the ID, but the secret access key, is when you create the keys. You can't recover them later, but I've downloaded my secret access key. However, if you need to create new ones, there's no limit regarding when or how many times you can create new access keys. So I'll delete my second active access key by clicking the X beside the access key. I'll select delete, and we're good. Now I can create a new access key by clicking Create Access Key. The access key ID is available. I'll highlight it, right-click, select Copy. Let's go back over to PowerShell, and I'll right-click to paste that value in. Now, when I press Enter, I'm prompted for the secret access key itself. So let's go back to the browser. I'll click Show. The secret access key is selected, so I'll right-click and select Copy. And let's go back over to PowerShell. I'll paste that in. Okay, and now I specify default region name. And my default region is US-East-1, which is North Virginia. Okay, pressing Enter, I'll specify default output format. Now this could be JSON, YAML, text, or table. It just depends on what you're using the specific output for. For our purposes, we'll specify JSON and press Enter. Okay, so first I'll clear. And now the CLI stores this information in a profile named default. And the information in the default profile is used anytime that we want to run an AWS CLI command that doesn't explicitly specify what profile to use. And the settings themselves are saved in a folder off the home directory named .aws. So if I do a listing by typing ls, I'll see that I have a .aws directory. Okay, so let's clear by typing clear and pressing enter. Now, incidentally, if you're on a Unix-based system, either Mac or Linux, then the .aws directory will be off your home or tilde directory. Okay, so now with those settings in place, we should be able to interact with our AWS account. One of the things that I would like to do is start an instance. So first, let's go over to the browser one more time. And now I'll close my Create Access Key dialog. And now I'll click Services, and I'll select EC2. I have 0 running instances, so I'll click on Running Instances. And both are in the state of stopped. So I'm going to grab the instance ID for my web server by first selecting the instance that I am interested in, and then under Description, beside Instance ID, I'll click the copy icon. Now I'll go back over to PowerShell, and now I'll specify the command aws ec2, that's the service that I'm accessing, and I want to start an instance, and the command here, start-instances. Then I need to specify an instance ID, and the parameter here is --instance-IDs. And now space, and I'll right-click to paste the instance ID in here, and this can be a list. We could start a number of instances if we wanted to. Okay, so now let's press enter. And now it's starting. Let's go over to the browser. We'll refresh. And the web server is now in a pending state. All right, and now the web server 1 instance has been started and is running. So let's go back to PowerShell. We don't want to leave a running instance if we don't need to, so first we'll clear. And now I'll up arrow to bring back the last start-instances command, and I'll replace start with stop. So the command is aws ec2 stop-instances, and again I use the instance IDs parameter and specify the instance that is now running. So now if I press enter, the message comes back saying that it's currently running. So now let's go back over to the browser. We'll refresh, and it should say stopping, and it is stopping. So we've successfully configured the AWS CLI so that we can securely interact with our AWS account using the CLI. In this demo, we'll configure an IAM role for AWS services. And the objective here is to configure the role and the policies behind the role for an EC2 instance to call an AWS service on our behalf. All right, I've signed in to AWS Management Console as an admin user. Under Recently Visited Services, I'll click IAM to go to the IAM dashboard. And in the left navigation menu, I'll click Roles. On the Roles page, there's some additional information about roles, as well as the currently existing roles, of course. So let's create a new role by clicking Create Role. And now we select the type of trusted entity first. And the first selection is AWS Service, which is the type of trusted entity that we'll employ in this demo. But we also have another AWS account as the trusted entity, a web identity, as well as federation. Now, as mentioned, we're going to choose the AWS Service trusted entity, and one of the most common use cases is with EC2. So we want to allow the EC2 instances to call other AWS services on our behalf. So let's click EC2 to get started, and then click Next Permissions. Now, we're going to create permissions that will allow for S3 full access. So that's Simple Storage Service, full access. So in the search box I'll type S3, and in the resulting list, I see a couple of managed policies, Amazon S3 Full Access and Amazon S3 Read-Only Access, as well as a couple of others. We're going to go with a full access though, so let's click the checkbox beside full access. Click Next Tags. We won't worry about tags at this point. Click Next Review. Now we'll give the role a name, and we'll call this S3-Full-Access. And the role description speaks for itself. That was filled in for us automatically. We'll leave it as is. We see the trusted entity is the AWS service EC2. We also see a listing of the policy, and we're not going to set any permissions boundaries in this demo. So we're ready. Let's click Create Role. And now we see the role has been created. So let's drill down into the role by clicking on S3 Full Access. And now we'll click to expand S3 Full Access. Scroll down and see the policy in JSON format. So basically, we have an effect, which is allow. We have the action, which is S3, and we are allowed any action, that's the asterisk, with respect to S3, that's full access, and any resource with respect to S3. So we've successfully created an IAM role for AWS services, and in this case, we've configured the IAM role and linked policies for an EC2 instance to be able to call S3 services on our behalf. In this demo, we'll attach an IAM role to an EC2 instance. I'm signed in to AWS Management Console with my admin user. I'm going to click to go to the IAM dashboard, so I'll click IAM, and I'll click Roles, and I'll scroll down, and I'll click to review the S3 Full Access role that I've created previously. So clicking to open S3 Full Access, and now to expand it, I'll click the arrow beside S3 Full Access, and I see the policy summary. This is for the S3 service. It's full access, all resources, and in JSON format, it looks like this. So lines 5 through 7 basically define the statement, the effect, action, and resource in this case. All right, let's go back to AWS Management Console. We'll click EC2 to go to the EC2 console. We'll click on Running Instances, and we have no running instances. So let's click Launch Instance. And now we're going to choose the Amazon Linux machine image, not Linux 2, because the default image includes the AWS command line tools. We're going to associate the IAM role with our instance. We'll launch the instance, then we'll use the IAM role permissions to interact with S3. After all, we have full S3 access. So basically what we're doing is providing access for the EC2 instance to be able to do whatever is required in terms of accessing S3 to maybe make a bucket, list the bucket contents, remove buckets, and so on. Okay, so let's go ahead and click Select beside the Amazon Linux machine image. We'll click Next Configure Instance Details, leaving the T2 micro selected. And now for IAM role, let's click to expand the list box, and we'll click to select S3 Full Access. Now the rest of the values we'll leave at their default, so we'll just click Review and Launch. And click Launch. Now we'll choose the existing EC2-key pair, click the Acknowledge checkbox, and click Launch Instances. Scrolling down, click View Instances. And our new instance is pending. All right, while it's pending, let's go over to PowerShell. We're going to access the S3 service by typing AWS S3 and the various commands that we're going to use. But we're not going to do that from here. Remember, we're launching this EC2 instance. So we're going to connect to the EC2 instance from here, and then we're going to perform actions on the S3 service from the EC2 instance. Okay, so now let's go back to the browser and see that the new instance is indeed in a running state. So let's click to select the instance and we'll click connect. Let's highlight the connect string. We'll right click, select copy, and now let's go over to PowerShell. So first I'll go into my downloads folder. That's where the key pair is located. And I'll right click to paste the command in and press enter. Type yes to confirm that we want to connect, and we're connected. So let's type clear, and now the first thing we'll do, we'll sudo su dash, and basically that will allow us to operate as root. All right, so now we're running as root. Now, to interact with S3, we type AWS S3 and then the rest of the command. And B is to create or make a bucket. And the bucket has to be a unique name across the region. So S3:// and we'll call this Joe Bucket 9999. And we have to specify the region with the -- region flag, and the region is US-East-1. Pressing enter, and it appears as though it worked. So let's do a listing. So that's AWS S3 LS, and there's our bucket that we created. Now we have an empty bucket, so we should be able to remove the bucket. If it was not empty, then we wouldn't be able to delete it. But let's delete it, and we'll use the RB command for that. So that's just AWS S3 RB and the name of the bucket that we want to remove. Pressing enter, and done. So now if we up arrow to bring back the listing, we'll see that it returns nothing because we've deleted it. So we successfully attached the IAM role to the EC2 instance, allowing it to interact with full permissions with the S3 service. In this demo, we'll simulate the launch of an instance to test profile permissions from the AWS CLI. In some scenarios, we would just like to make sure that we have the proper permissions set up, but not actually run a command. Some AWS CLI commands contain the --dry-run command option, which simulates API calls. Essentially, the dry run command checks whether you have the required permissions in order to perform the action that you're requesting, without actually making the request. It provides an error response either way. But if you have the required permissions, the error response is dry run operation. Otherwise, the error response is unauthorized operation. I'm signed into AWS Management Console and I'm on the IAM dashboard. I'm signed in as an admin user. We're going to examine the user that we'll use in this demo. So in the left navigation pane, I'll click Users. I'll click Dev User. And the summary information for this user appears, and under the Permissions tab, I'll see that I've got a policy of IAM user change password, which is set up when creating a user. Notice also under Attached from Group, the words Show One More. This is a link to another policy that this user has applied against their account by virtue of their membership in the Dev Restricted Group. So I'll click on Show One More. Now this is an AWS managed policy from the Dev Restricted Group, and it's Amazon S3 full access. So this user has S3 full access, but not EC2. Okay, so now let's go over to PowerShell, where I have my AWS CLI configured. Now we'll configure a new profile. And to do that, I'll type AWS configure -- profile, and the username is dev-user. So I'll use that as the profile name as well. So pressing enter. Now I have to provide the 4 pieces of information including the access key ID, secret access key, the default region, and the output. Now, I've previously downloaded the credentials for this user, and I've got those credentials opened in Notepad. So I'll go ahead and grab the access key ID first. So I'll highlight it, right-click, select copy, over to PowerShell, paste that in by right-clicking. Now I need the secret access key, so back over to Notepad, I'll grab that. Right-click, select copy. Over in PowerShell, right-click to paste that in. For default region name, I'll use US-East-1. And for default output format, I'll just specify JSON. And press enter. Okay, so now I'll clear. And now I will have two profiles in the two files under the .aws directory. So if I do a listing here by typing ls, I'll see that there's two files, config and credentials. Now if I cat out config by typing cat config, it responds with not only the default profile that I set up earlier, but now we've got a dev user profile as well. So I'll clear, and now I'll cat out credentials. And it's similar with credentials. I have my default credentials and my dev user credentials. Okay, so that's how you set up multiple profiles. Now, I'm going to clear one more time. Now, I'll try to launch an instance with the dry run parameter. And I'll use the dev user profile. Okay, I'm going to right-click to paste the command in, and then I'll go over the command line by line. The first line, AWS EC2 run-instances. We're telling the AWS CLI to access the EC2 service, and the run-instances command tells the service to run a new instance. The backtick at the end of the first line allows me to spread this command over multiple lines so that we can go over them line by line. Line 2 is --dry-run, which is the dry run option. Then I specify an image ID, an instance type, and I also have to reference the profile that we created, dev-user profile, and then I specify a key name. Recall that I said there's an error response either way. So the error response here is unauthorized operation. When calling the run instances operation, you are not authorized to perform this operation. And this is followed by an encoded error message. We won't look at that at this point. We'll look at that later in this course. Okay, so what happened? Well, the user doesn't have access to EC2. So that's why we got the error that we did, unauthorized operation. Otherwise, if we had the required permissions, it would have said dry run operation. Okay, so let's clear. Now let's go back over to AWS Management Console. Now, under policy type on the summary page for this user, the group dev restricted is accessible from here. So I'll just click to open the dev restricted group. Currently, this group only has access to S3. So I'll click attach policy and I'll search for EC2 full access. Now I'll click the checkbox to select the Amazon EC2 full access policy and click attach policy. Okay, so now this user, because of their membership in this group, should be able to access the EC2 service. So let's go back over to PowerShell. I'll up arrow to bring the command back, and I'll press enter. And we see the dry run operation error message. It tells us also that the request would have succeeded, but dry run flag is set. So what we've done is we've successfully simulated the launch of an instance to test the profile permissions from the AWS CLI. In this demo, we'll use the AWS Security Token Service to decode a message from the CLI. The AWS Security Token Service, or STS, is a web service that allows us to request temporary limited privilege credentials for Iam users or federated users. But an interesting action that we can perform with STS is decode authorization message. This action decodes additional information about the authorization status of a request from the encoded message that's returned when making certain AWS requests. I've signed into AWS Management Console with my admin user, and I've navigated to the Iam dashboard. In the left navigation menu, I'll click Groups, and I'll click on Dev Restricted Group. And there's one user in this group. I'll click the Users tab, and that's the dev user. On the Permissions tab, I have two policies attached, EC2 Full Access and S3 Full Access. Let's remove EC2 Full Access. So I'll click Detach Policy in line with EC2 Full Access, and in the Detach Policy dialog, I'll click Detach. Okay, so now this user, dev-user, no longer has access to the EC2 service. Now, on my taskbar, I've pinned the Visual Studio Code icon. So I'll click to open Visual Studio Code. All right, and Visual Studio Code opens to the .aws directory. That's where I last was working when I had Visual Studio Code open. I also had the terminal open, the PowerShell terminal that is, open to the same .aws directory. Okay, first I'll type clear to clear the terminal, and now I'm going to right-click to paste an EC2 run-instances command into the terminal session. Okay, and it generates an error. Now, with this command, I'm using the AWS CLI to call the EC2 service with the run-instances command. I'm using the dry run option, and I'm also specifying the dev user profile, whom we know no longer has access to EC2, having just removed that access. Now, there is an unauthorized operation error telling us that there was a problem, but we also have this entire encoded authorization failure message. So let's grab this message by highlighting the entire encoded message, and now right-clicking in PowerShell copies that to the clipboard. Now I'll type clear, and now let's decode the message by typing AWS STS decode -authorization -message. I'll use the --encoded -message flag, space, then I'll right-click to paste the encoded message, then --output. I'll specify text, and the right arrow or greater than sign, and message.json, because we'll append the decoded message into a file named message.json. Okay, so pressing enter, and it's done. And now in the Visual Studio Code Explorer, I see a new file, message.json. I'm going to double-click to open it. And now, if I right-click in the body of the document, and I'll select Format Document, and that formats the document in a human-readable JSON format. And I've got a lot of information here. It tells me that allowed was false. Explicit deny was also false. Scrolling down, I've got information about the context, the principal, the action, the resource, the instance market type, the AWS account, the availability zone. So a lot more information than just the unauthorized operation message. So we've successfully used the security token service to decode a message from the CLI. In this demo, we'll retrieve metadata about an EC2 instance using the Instance Metadata service. Instance metadata is available for us to grab from a running instance outside of the EC2 console or the CLI, and this avoids having to assign an IAM role specifically for that purpose. I've signed into the AWS Management Console and navigated to the EC2 dashboard with my admin user. Under Resources, I have one running instance. Let's click to open the Instances page. I have a machine named Web Server IMDS, and IMDS stands for Instance Metadata Service. Now let's just scroll down and see what we have with this machine. I'll grab the bottom part and pull it up a little bit so we have more room. So I have a public DNS. I also have the security group launch wizard 4. Let's look at the inbound rules. Okay, so I've got port 80 open and port 22 open, so we're good to go. All right. Now, down in the taskbar, I'll click the Visual Studio icon to bring up Visual Studio. I've opened a terminal prompt, and I've SSH'd into the machine that we are looking at. Now, I've also got a couple of IMDS v1, and I've got an IMDS v2 command. So in line 2, I'm just using the curl utility with the URI for the instance metadata. So that's http://169.254.169.254/latest/meta-data/. So let's grab line 2. We'll highlight everything on line 2. Right click, select copy. Now down in the terminal prompt where I've SSH'd into my machine, I'll right click to paste the curl command in and press enter. And the response is all the categories of metadata. So we have AMI-ID, we have block-device-mapping, and notice the different types of values. So we have the individual values, but any values that have a slash at the end, that means that there's more information underneath. So for example, host name, well, that's a value, but identity credentials will have other values underneath it. Okay, and now we're going to look at something like that with the next command. So in line 3, this curl calls on the latest metadata, but it also looks at the identity credentials and the security credentials for this EC2 instance. So let's highlight that command, right-click, select copy. Now down in the terminal prompt, we'll type clear, and then right-click to paste that curl command. And it responds with the security credentials that were used on this instance. Okay, so now I'll type clear again and press enter. Now, looking at lines 8 and 9, this is IMDS v2. And with version 2 of the instance metadata service, you need to acquire a token first. And you do that by using a put HTTP request with the URI /latest/API/token. So that gets us our token, and we use the -H parameter to send a custom header and apply a TTL of 3600 seconds or 1 hour. Then in the second part of the command, we're using curl again. We're passing the custom header with the token this time, and we're going to pull up the metadata about the user data that was used to bootstrap this machine. Okay, so let's highlight lines 8 and 9. Right-click, select copy, down in the terminal, right-click, and now press enter. And it responds with the user data that was used to bootstrap this machine. Incidentally, I also have that over on my second tab, Custom Web Page. So basically, lines 1 through 6 include the shebang, and then I'm installing and configuring Apache Web Server. Then lines 9 through 12, this is where I'm using my instance metadata to, for example, pick up the instance ID, to pick up the instance type, to pick up the availability zone, as well as the public IPv4. Then, lines 15 down through 23. Well, here I'm creating an index.html file for the web server, which will splash the information that I've obtained to the home page when the user navigates to the home page. And then finally, lines 26 and 27, I'm just basically setting up a permanent change to the bash prompt, a little bit smaller, more convenient version. All this information was used to bootstrap the machine. That's what we pulled up when we did the user data query earlier, a few moments ago, right? And so now let's go and have a look at the web page and see what happens. when we navigate to the web page. So over to the EC2 dashboard and the instances page, I'll grab the public DNS by clicking the copy to clipboard icon beside it. Now I'll open a new tab, right click, and select paste and go. And there's all our information. Now, this t2.micro value was obtained using the instance metadata, as was the instance ID, as was the availability zone, and finally, also the public IP address. So you get a sense of how much information you can actually grab using the instance metadata service. In this demo, I'll install and configure an AWS SDK. To get started, I've signed in to the Aws Management Console as my admin user. I've navigated to the EC2 dashboard, and under Resources, I have one running instance. I'll click to open the Instances page, and I have a web server running. Now, normally I would connect from here. I've already connected with Secure Shell, so I'm not going to go through that again at this point. Instead, I'm just going to go right over to Visual Studio Code. So down on my taskbar, I'll click to open Visual Studio Code. And in the bottom part, in the terminal, I've already connected to this machine with SSH, as mentioned. So now I can start to work with this machine. Now, initially, you should really update the packages on the system with sudo yum update. So I'll type sudo yum update, but I've already updated this machine as part of the user data that I specified when I bootstrapped this machine. But I'll do it again just to, so I'll type sudo yum update and press enter. And the system tells us that no packages were marked for update, which is just fine. Now I'll clear the screen by typing clear and pressing enter. And so now, from lines 4 through 7, I describe what we're going to need to do to get started installing Node Version Manager, first of all, because I'm going to install the AWS SDK for JavaScript. And I need Node for that. Node Package Manager, actually. But Node and Node Package Manager kind of go hand in hand, right? So I'm also installing Node Version Manager because that way I can switch between node versions whenever I need to. Okay, so line 6, I'm using the curl utility. Now the -o means output, and the dash, as specified in the comment, means that we force the output to standard out because we're just downloading the install shell script for Node Version Manager. We don't need any output to go to a specific file. With line 6 selected, I'll right-click, select Copy, and I'll paste that down in the terminal by right-clicking. Now I'll press Enter. All right, and now the NVM script has been downloaded. Now, in order to activate Node Version Manager, the reply from the installer tells us to run 3 lines. I'll highlight these 3 lines. So I'll right-click to copy that to the clipboard. Now I'll clear the screen by typing clear and pressing enter. And now right-click again to paste those 3 commands in and press enter and done. So now let's clear one more time. And now let's type nvm -- version. And it tells us that we've got version 0.34.0. Fine, so let's clear, press enter. Now we need to install Node. And to do that, we use Node Version Manager. So that's nvm install Node. And press enter. Excellent. So let's clear again. And now let's type node -- version. And now let's type npm -- version. Okay, so both have been successfully installed. So let's type clear, press enter, and now to install the AWS SDK. Now this is a Node Package Management module, an NPM module. So ideally what we want to do is start a project by typing npm init and pressing enter. And this walks us through creating the package.json file. For the package name, I'm just going to call this s3-sample. So I'll type s3-sample. The version, I'll just press enter. That's fine. I won't put a description in. At the moment, it's expecting the entry point to be a file named index.js. I'll change this to app.js, typing app.js, press enter. Test command, I'll leave blank, just press enter. There is no Git repository for this code. Keywords is fine. Author, I'll just put my initials. And for license, I'll press enter to accept the default. And I'll type yes to accept these values. Okay, so now let's clear, press enter. So now if I do an ls, I'll see that I now have a package.json file on this machine. So now I'll type clear. So now we need to install the SDK. And to do that, I'll just type npm install aws-sdk --save. Save it as a dependency. Okay, and now pressing enter. Ignore the warnings. I'll just type clear. And now if I cat package.json, I'll see that I now have the AWS SDK version 2.678.0 as a dependency. So we've successfully installed and configured the AWS SDK for JavaScript on this server. In this demo, we'll use an AWS SDK to interact with AWS services. I've signed into my AWS Management Console and I've navigated to the EC2 dashboard and then to my instances. I have one instance. It's a web server. Now I have the ports set up, so I have port 22 and port 80 open. Okay, scrolling down under the description tab, I have no IAM role currently associated with this web server. Now, that can be a problem depending on what you're doing, because we want to allow this machine to interact with the S3 service. That's what we're going to do in this demo. And that's just security best practice to use an IAM role for that purpose, because after all, we definitely do not want to use a developer's credentials on this machine and have to maintain those credentials in that manner. It's just not good practice. So the first thing that we'll do, with the instance selected, click Actions, point to Instance Settings, and select Attach Replace IAM Role. Right now, there is no role. Click the down arrow to open the list box. Here's S3 Full Access. I'll click on that, and click Apply. And now close. Excellent. So now, again, if I check under Description, I'll see that I now have an IAM role for S3 Full Access associated with this machine, so no need to copy credentials up to the machine. Okay, so now let's click Actions, point to Instance State, and select Start. And when the Start Instances dialog appears, click Yes, Start. And now I'll click the refresh icon, and the instance state is reported as pending. So now once that is done, we'll SSH into it using my PowerShell terminal prompt within my Visual Studio Code editor. Okay, and now the machine is running. So again, with the web server selected, click Connect. And in the Connect to your instance dialog, I'll triple click to select the Secure Shell connection string. Right click and select Copy. Down in the taskbar, I'll click to open Visual Studio Code. And in the terminal, I'll right click to paste that SSH connection string and press Enter. Type yes, and we are connected. So I'll type clear. All right, so now I have my application ready to go. So let's just have a look at the code. I'll reduce the size of the terminal window. Now let's scroll up and check out what's going on here. So first, lines 1 through 3, I'm importing the AWS SDK, that's one of the main things that you should understand with this particular demo, is that you need to require that AWS SDK. This is a JavaScript SDK after all, so we need to require it within our app. Then we're going to use the UUID module. And we're using the UUID module because we need to have a unique bucket name across the Amazon S3 service. And we're doing that by calling the UUID module and appending a unique ID to a familiar value. Now, line 6, it's not absolutely necessary here, but I just wanted to make sure that you were quite aware of this. By default, when you're working with the AWS SDK, the default region is US-East-1. Now, this is not strictly necessary here because we're working with S3 and it's global. Now, lines 9 and 10, here we set up the unique name for the S3 bucket and we set up a name for the uploaded object key. Then line 13, we create a bucket promise. So basically with the call to the S3 method, we specify the API version, then create bucket, we specify the bucket name, and then we specify a promise. Because in Node and JavaScript, we want to make sure that we're going to get our response back before we continue on, or we handle it with a promise, and that's what we're doing here. Then from lines 16 on down to 29, we're basically taking care of all the promise states. So we have a promise state where the promise was met. Then in that case, we're going to splash a message to the console that says the data was successfully uploaded and the bucket name and key name. Otherwise, we specify an error to the console. Okay, so let's make the terminal a little bit bigger by dragging it up. And now to get started, first I'm going to have to install UUID. And to do that, I type npm install uuid-save and press enter. Okay, done. Now to run the app, I simply type node app.js and press enter. All right, and the message comes back that data was successfully uploaded to my bucket with the UUID that makes it a unique identifier and the key name. So now let's go back over to AWS Management Console. So down in the taskbar, I'll click the icon for my browser. I'll click to close the Connect to Your Instance dialog. And now click Services, under Storage, and click S3. And there is our bucket name under the list of buckets. Now, if we drill down into the bucket, we'll see that we have sample.txt. So we've successfully used the AWS SDK for JavaScript to interact with the S3 service on AWS and create a new bucket and a new object under that bucket. So in this course, we've examined the installation and use of both the AWS Command Line Interface, or CLI, and the AWS Software Development Kits, or SDKs, to interact with AWS Cloud Services. We did this by exploring the methods for interacting with AWS services and resources, including the AWS CLI, SDK, and APIs, how to install and configure the AWS CLI on Windows 10, Ubuntu Linux 18, and Mac OS X development machines, how to attach IAM roles to an EC2 instance and configure IAM roles and policies for an EC2 instance, and how to use the CLI to simulate the launch of an instance. We went on to explore how to use the AWS Security Token Service, or STS, to decode a message from the CLI, how to use the Instance Metadata Service to obtain EC2 instance metadata. We also explored how to configure an AWS SDK, and how to use an SDK to interact with AWS services. In our next course, we'll move on to explore how to design and implement AWS cloud storage, including the use of Elastic Block Storage, or EBS, Elastic File System, EFS, and Amazon Simple Storage Service, S3, as well as S3 buckets. In this video, we'll explore Amazon EC2 instance stores. Instance stores offer temporary block-level storage solutions for EC2 instances from disks that are physically attached to the host system, that is, the AWS physical hardware. Instance stores are ideal as a temporary storage solution, particularly for information that sees frequent changes, meaning buffers, caches, and other types of temporary data storage requirements. Different instance types support different numbers of devices and instance store sizes, and virtual devices that make up instance store volumes are considered ephemeral 0 to 23. So if an instance type supports only one volume, then it's ephemeral 0. If it supports 2 devices, then it's ephemeral 1. If it supports 24, then it's ephemeral 23. Instance store volumes may be specified only when an instance is launched, and you cannot detach one from an instance to attach it to another instance. Instance stores persist data only while its associated instance exists and across reboots. However, the data is lost if the physical disk drive fails. It's also lost if the instance is stopped or if the instance is terminated. So, instance stores are not for long-term data storage. Instance store volumes are specified at launch, and then they're formatted and mounted before using them. Instance store volumes cannot be made available after an instance is launched. Now, some instance types offer a high random I/O performance. They're using NVMe or SATA-based solid-state drives. This is ideal when you require storage with very low latency. However, again, since the data will not persist when the instance terminates, this is only a valid option when you don't need the data to persist when the instance terminates. EBS volumes and instance store volumes get added to an EC2 instance using a block device mapping, which includes a device name and the volume that it's mapped to. The default block device mapping is determined by the machine image being used, but you can also specify a block device mapping for an instance when it's launched. A block device mapping specifies the root volume for an instance, and the root volume can be an Amazon EBS volume or an instance store volume. In addition, the root volume is mounted automatically, and when the root volume is an instance store volume, the maximum size is 10 gigabytes, but it does vary by machine image. All the NVMe instance store volumes supported by an instance type are automatically enumerated and assigned a device name when the instance is launched. Now, specifically for instance store volumes using NVMe devices, you use the lspci command to list them after connecting to the instance. In addition, data on an NVMe-based instance store is encrypted using a hardware module on the instance. Some instances support instance volumes using non-NVMe SSDs to provide elevated I/O performance. All instance store volumes may be used for Linux swap space, which is a feature that allows storage space to be used when a system requires more RAM than it was allotted. The Amazon Linux machine images automatically have swap space enabled. Some machine images may require additional configuration in order to see and use swap space, though. To enable and use swap space, the process involves unmounting the instance store volume if it is mounted, then configure the swap space area on the device using the mkswap command, then enable the new swap space, then edit the /etc/fs tab file to ensure that the swap space is automatically enabled at system boot. It's important to understand that because instance store volume data does not persist when the instance is stopped, if you absolutely must stop and restart an instance that has been configured as outlined here, to use instance store swap space, then the process must be repeated. On some instance store volumes, due to how Amazon EC2 virtualizes disks, the first write is slower than subsequent writes. While this may be okay for some applications, if you need the best disk performance possible, it is recommended that drives be initialized first by writing once to every location on a drive before it's put into production. This is done by unmounting the drive and using a series of commands, and this can be performed on all drives simultaneously. Configuring RAID drives initializes them with a write to every location on the drive. In this video, we'll explore AWS Block Storage. Amazon Elastic Block Store, or EBS, offers block-level storage volumes with the lowest latency access from individual EC2 instances. EBS volumes can be attached to an instance in the same availability zone, and they're automatically replicated within the availability zone, so they're highly available and reliable, and the EBS service makes it easy to scale up or down. Common use cases for EBS volumes include using them as boot volumes, for databases, for streaming and log processing applications, for data warehousing applications, and for big data analytics. EBS provides two volume types, hard disk drive and solid-state drive-backed volumes. Hard disk drive-backed volumes are most applicable for large streaming workloads, the type where throughput is more important than input-output operations per second. Solid-state drive-backed volumes are ideal for transactional workloads where the most important metric is input-output operations per second, or IOPS. With Amazon EBS Elastic Volumes, the volume size can be increased dynamically. The performance can also be tuned, and the volume type can even be changed. And if the instance supports elastic volumes, this can be done without detaching the volume from the instance or restarting the instance. This means zero downtime. So there is no impact on performance. And one of the greatest benefits of this is that you can create volumes with capacity and performance criteria that exists today, and know that you can adjust the configuration as required on into the future. EBS volumes are backed up with point-in-time snapshots to protect and back up data. Snapshots can be used to create new EBS volumes, which are identical replicas of the snapshot on which they are based. Snapshots are incremental backups, so only blocks that have changed since the last snapshot are saved. The snapshot deletion process is managed by EBS and is implemented such that only the most recent snapshot is required in order to restore the entire volume. Data from an earlier snapshot that is deleted from the volume that snapshot is based on at some point later is still seen as being unique data on that earlier snapshot. The unique data, therefore, is not deleted unless all snapshots referencing the unique data are also deleted. EBS volumes are seen as network-attached drives. So optimized instances use an optimized configuration that sees the traffic between the EBS I/O and an instance separated from other traffic on the instance. Depending on the instance, EBS optimized instances may actually incur an extra charge. Amazon EBS supports encryption for all EBS volume types to address data at rest requirements concerning regulated and audited data. It uses 256-bit AES standard encryption and takes advantage of AWS Key Management Service. Encryption happens on the server hosting the EC2 instance. So data is encrypted in transit from the EC2 instance to the EBS store. Optimal performance for EBS volumes depends on the scenario. Some best practices include the fact that it's best practice to use EBS optimized instances because the dedicated network throughput just makes the performance of the volume more consistent, and the EBS volume traffic won't have to compete with other instance-based network traffic since the two are isolated. Another best practice is to understand performance calculations because, after all, depending on what you're trying to measure, the metrics may be vastly different. And it's also just best practice to consider the workloads when deciding on EBS volume configuration. The nature of the workload alone will have a direct impact on the choice of EBS volume type, the number of volumes, whether to use hard disk drive or solid state drive backed volumes. Is it IOPS or is it throughput? Finally, one last item of interest to take away is that you must be aware of how EBS volumes restored from snapshots must be initialized before they reach optimal performance, which can take some time and introduce latency in I/O operations. In this video, we'll explore Amazon CloudFront. Amazon CloudFront is a fast and secure content delivery network service. It provides data, applications, videos, and APIs globally and is integrated with AWS. Some of the benefits of this service include the fact that it's massively scaled and globally distributed, like many other services offered by AWS, meaning that it maintains excellent performance and availability for customers wherever they're located. CloudFront is also big on security, offering application and network level security and integrating with several security protection features from AWS. CloudFront may also be configured to leverage AWS Certificate Manager for managing SSL certificates. All of these are features that come by default with CloudFront. It's also very flexible, with many features that can be tailored to specific requirements, including the ability to move complex application logic geographically closer to end users for better responsiveness. CloudFront can be integrated with other tools and resources, including automation interfaces in support of DevOps and CI/CD. CloudFront also seamlessly integrates with other AWS services like Amazon S3, EC2, Elastic Load Balancing, and others, and all features may be configured using AWS Management Console or APIs. To configure CloudFront, you specify the origin servers. For example, a web server or S3 bucket. Objects are uploaded to the origin servers, and if an Amazon S3 bucket is used as an origin server, we can easily take advantage of S3's ability to finally control who has what level of access to the resources. Next, a CloudFront distribution is created, and this essentially specifies which origin servers CloudFront should get the resources from when they're requested by end users. We can also tell CloudFront to log all requests and when to make the distribution available. Next, a domain name is assigned to the new distribution by CloudFront, and this domain name is available in the CloudFront console. Note that you can also configure CloudFront to use your own domain name with your distribution. CloudFront transmits the distribution's configuration to all geographically distributed CloudFront edge locations where CloudFront maintains cached copies of the files or resources. CloudFront edge locations or points of presence are geographically dispersed to quickly serve up content to end users. CloudFront leverages regional edge caches, which are located between the origin server and the points of presence global edge locations. They serve content to viewers from a location closer to the user, which generally improves delivery speed or responsiveness of the content to the user. In order to ensure that resources are retrieved from their origins as fast as possible, CloudFront also keeps a persistent connection with the origin servers. There are a variety of ways that CloudFront can be accessed, including the Aws Management Console when you want to perform tasks manually, using the Aws SDKs. So if you're using a supported programming language, one with an SDK from AWS, then that SDK can be imported into your application to access CloudFront commands within your code. You can also access CloudFront commands using the AWS CLI, the AWS tools for Windows PowerShell, which is similar to the AWS CLI but with PowerShell commandlets. And you can also access CloudFront through the CloudFront API when an SDK isn't available for your programming language. In this video, we'll explore AWS file storage. Amazon Elastic File System, or EFS, is scalable file storage with a standard system interface for Amazon EC2 service. EFS can be mounted on multiple instances simultaneously and can scale up to the petabyte range. EFS, you define mount targets, which are network file system endpoints created in the VPC. The endpoints include a DNS name and IP address, and both can be used in a mount command. The file system is the principal resource offered by Amazon EFS. It's where files and directories are stored. Each account can have up to 125 file systems. There are multiple options for accessing the Amazon EFS file system. First, through the EC2 service. Accessing a file system from an EC2 instance involves mounting the file system using standard mount commands. A file system exists within a region, and the file system spans all availability zones in that region. Once the file system has been mounted, data is accessible from all availability zones in the region. Using AWS Direct Connect, you can mount on-prem servers to Amazon EFS. In this scenario, you still use the same mount commands. Typical use cases include using EFS in combination with Direct Connect for backup and disaster recovery, for bursting, or migration. You can sync files from an existing file system to an Amazon EFS file system using AWS Data Sync. It's possible to synchronize not only file data, but also file system metadata like ownership and access permissions. You first must download and deploy a sync agent from the Amazon EFS console. The sync agent is offered as a virtual machine image or an Amazon machine image. Amazon EFS can be used for a wide range of performance characteristics, including high throughput and parallel I/O, and for low latency and serial I/O. It does this by offering two different performance modes. A general performance mode, which is the default mode, and with general purpose mode, you get the lowest latency for file operations, but with a limit of 7,000 operations per second. The Max I/O performance mode offers extreme ability to scale throughput and IOPS with somewhat higher latencies as a trade-off. In most cases, you can easily set up Amazon CloudWatch metrics to gauge whether you're regularly reaching the IOPS limit in general purpose mode, in which case you may want to consider moving to Max I/O performance mode. Security can be implemented in multiple layers with Amazon EFS file system by controlling both inbound and outbound network traffic in the file systems using both security groups and network ACLs. By managing file and directory access using standard POSIX permissions, and by providing administrative API access to file systems using IAM permissions. In this video, we'll explore AWS Object Storage. Amazon Simple Storage Service, or S3, provides efficient, cost-effective object storage. Examples of objects are documents, videos, and images. Objects are stored in containers called buckets. Amazon S3 bucket names must be globally unique with the namespace shared across all AWS accounts. S3 delivers content using API calls. It's very scalable, it's very reliable, and it offers low latency data storage. You can store virtually any number of objects on Amazon S3, so long as the size of the object is at least 1 byte or less than 5 terabytes. You can use a file splitter to upload large files in chunks to S3. Then if the file is needed later, the file chunks can be downloaded and reassembled. An object is really just a collection of facet attributes. First, there's the key. The key is the unique identifier of an object within a bucket. Combining the bucket, the key, and the version ID uniquely identifies every object in S3. So then within a bucket, a key and version ID uniquely identify an object with versioning enabled. Otherwise, there is just one version. The value is the content being stored. Metadata is a collection of name-value pairs that describes the object. User-defined metadata is assigned when the object is uploaded by the user, while system metadata is maintained by the S3 service itself. For example, content type is system metadata. Sub-resources are defined by S3 and are always associated with some other entity like a bucket or object. These include an access control list, which is a list of permissions granted, and torrent, where S3 supports the BitTorrent protocol. Object tagging offers a way to categorize storage, and tags consist of key-value pairs, and you can associate as many as 10 tags with any specific object. Amazon S3 offers different storage classes to choose from. They offer varying levels of durability, availability, and performance. Amazon S3 Standard is for frequently accessed objects. This is the default storage class, and it's designed for performance. Standard is a highly durable and highly available storage solution with low latency and high throughput. S3 Standard is designed to realize a durability of 99.999999% of objects, withstanding the loss of data in 2 facilities, and an availability of 99.99%. Typical use cases for S3 include big data analytics, cloud applications, content distribution, dynamic websites, and mobile and gaming applications. Amazon S3 Standard Infrequent Access is designed for data that is accessed less frequently, but still provides rapid access when required. It has the throughput, low latency, and durability of S3 Standard, but lower storage and retrieval fees with low retrieval times. It is designed for 99.9% availability. Typical use cases include backups, long-term storage, and storage for disaster recovery. S3 One Zone Infrequent Access is similar to standard infrequent access. However, data is stored in a single availability zone. It costs 20% less than standard infrequent access, but if that availability zone suffers a catastrophic failure that leads to destruction of the data, then it's permanently lost. And then there's Amazon S3 Glacier. This is a very low-cost storage service for data archiving. It is secure and it's durable, offering the same high durability as Amazon S3, but whereas S3 Standard offers immediate retrieval times, S3 Glacier's retrieval times are significantly longer. There are 3 retrieval speed options to choose from, ranging from minutes to hours. S3 Glacier's low cost make it attractive as an archive for long-term storage for regulatory and data retention policy. And finally, we have reduced redundancy storage. This service is an S3 storage option allowing customers to store data of a non-critical, reproducible nature, but at reduced levels of redundancy than Amazon S3 standard storage. It's still a highly available storage solution, typically used for distributing or sharing content that is safely and durably stored in another location. S3 reduced redundancy storage stores objects on multiple devices over multiple facilities and has up to 400 times the durability of a common disk drive. It's designed for 99.99% availability, which is the same as Amazon S3 standard with a durability of 99.99%. It's designed to withstand the loss of data in a single facility. In this video, we'll explore cloud data migration. Data is, of course, foundational to any business initiative, and cloud deployment is an excellent example of the need for planning a smooth transition when migrating data on-prem to the cloud. AWS offers a suite of tools and resources to help migrate data through online, offline, unmanaged, and hybrid models. Let's take a look at these models. First, let's consider data transfer via online methods. AWS offers a number of online methods to simplify and ease the transfer of data into and out of AWS. First, there's the data transfer service AWS DataSync. DataSync helps automate the movement of data between on-prem storage and various AWS storage services, including Amazon S3, EFS, and Amazon FSx for Windows File Server. It automatically manages a lot of data migration tasks that can sometimes become bottlenecks to the migration process. The AWS Transfer family offers a fully managed support service for file transfer to Amazon S3 using technologies like Secure File Transfer Protocol, or SFTP, File Transfer Protocol over SSL, FTPS, and File Transfer Protocol, FTP. There's Amazon S3 Transfer Acceleration, which accelerates transfers to Amazon S3 over the public internet. With Transfer Acceleration, you just alter the endpoint used with your S3 bucket, and acceleration is automatically applied. Amazon Kinesis Data Firehose helps load streaming data into AWS. Firehose can automatically load streaming data into Amazon S3 and Redshift. It's a fully managed service that automatically scales to accommodate the throughput of an organization's data. The AWS Partner Network, or APN, is a global program offered by AWS. These partners offer technology and consulting services that can help migrate data online. For offline data transfer, Amazon offers the Snow family. First, there's AWS Snowball, which is a data transport and edge computing device for petabyte-scale data transport and edge computing that offers onboard storage and includes Snowball Edge storage-optimized devices, supporting both block storage and Amazon S3 compatible object storage, and 40 virtual CPUs, and the Snowball Edge compute-optimized devices providing 52 virtual CPUs, block and object storage, and an optional graphical processing unit. AWS Snowmobile is a 45-foot-long ruggedized shipping container for transferring extremely large amounts of data into and out of AWS. It addresses issues related to high network costs, transferring such large volumes of data, long transfer times, and security concerns. AWS hybrid cloud storage architectures connect on-prem systems to cloud storage. AWS Storage Gateway is a hybrid cloud storage service that can help to ease the implementation of AWS storage. With Storage Gateway, you can enable on-prem applications to use AWS storage for several uses, including migration. there are three different types of service with Storage Gateway. There is File Gateway, Tape Gateway, and Volume Gateway. We'll visit these in some detail shortly. First, let's talk AWS Direct Connect. This is a hybrid solution that establishes a dedicated physical connection to effectively boost data transfers from an organization's network to one of the AWS Direct Connect locations. The dedicated connection may be partitioned to create multiple virtual interfaces using 802.1q VLANs. This allows the same connection to be used for accessing public resources as well as private resources, all the while preserving the network separation between the two environments. Storage Gateway provides three different types of gateways. A file gateway is essentially a file-based interface to Amazon S3, integrating a cloud service with a virtual machine that presents a virtual software appliance deployed into on-prem environments. It kind of acts as a network file system mount of Amazon S3, providing access to data directly in Amazon S3 from on-prem as a file share. A volume gateway enables the mounting of cloud-based storage volumes as iSCSI devices from on-prem application servers. It supports two modes, cached mode and stored volume mode. In cached mode, data is stored in Amazon S3 and frequently accessed data is cached by the gateway locally. Stored volume mode has data stored locally backed up asynchronously in the form of Amazon EBS snapshots stored in Amazon S3. Then there's Tape Gateway. Tape Gateway can back up data to migrate from physical tapes to durable archive backup services like Amazon S3 Glacier. With Tape Gateway, data is stored and archived on virtual tapes in AWS. One of the primary use cases is migrating data from tapes into a more durable storage medium that still behaves like a tape. AWS provides command line interface tools or easy script to migrate data from on-prem to AWS cloud storage. AWS supports the use of rsync, an open source utility providing fast file transfer combined with third-party file system tools to copy data into S3 buckets directly. There are AWS CLI S3 commands which can be used to move data directly into S3 buckets, and the AWS CLI S3 Glacier commands, which again can be used to move data directly into S3 Glacier vaults. In this demo, we'll work with AWS S3 buckets. We'll create and use S3 buckets to store and retrieve objects. Okay, I have Visual Studio Code open, and I have it open to my AWS projects directory. I also have the readme.txt file and the app.js file for my application open in the editor. In the readme.txt file, it tells me that I need to type the command npm install -- save in order to install all the dependencies. So down in the terminal prompt in Visual Studio Code, I'll type npm I, which is an alias for install, -- save. Pressing enter. All the packages have been installed. So now I'll clear. And notice over in the File Explorer for Visual Studio Code, I now have a node module subdirectory, and all the packages that are installed in the node_module subdirectory are those listed in the package-lock.json and package.json. So if I double click to open package.json, I will see those packages here. So we have the AWS SDK and the UUID module. Okay, so let's close package.json by clicking the close icon on the tab for package.json. Now let's look at the app.js file. So first I import my required libraries in lines 2 and 3. Line 6 is absolutely not strictly necessary, but I have it here anyway. And lines 8 through 15 are very important. Now, I can successfully run this application on an EC2 instance with that EC2 instance obtaining an IAM role with full access to the S3 service. However, from my local machine, I need to go and grab those credentials from the config credentials that I set up when I configured the AWS command line interface here. So on lines 12 and 13, I'm splashing the access key ID and the secret access key to the console. I also splash the region to the console. Now, starting on lines 20 through 21, I establish a variable with the name of myBucket dash plus a unique identifier. That's why we pulled in the UUID package. Then I create a key name, sample.txt, and then on line 24, I create a bucket promise. Now, a promise is a proxy for a value that's not necessarily known when the promise is created. And this allows us to associate handlers with an asynchronous action's eventual success and the value that it entails, or the reason that it failed. This allows asynchronous methods to return values like synchronous methods. And rather than immediately returning the final value, the asynchronous method just returns a promise to provide a value at some point in time. And it can be pending, fulfilled, or rejected. Starting on line 27, that's where we take care of the states for this promise. So if we're successful, then we'll splash a message that data was successfully uploaded to, and the bucket name and the key name. And this is on line 35. Otherwise, if it failed, then we splash the error to the console. Let's get started by typing node app.js to run the application. Okay, great. So the access key ID, the secret access key, the region, and the message that the data was successfully uploaded to the specific bucket. And notice that we have the name myBucket with a UUID value. And that makes sure that we've got a unique identifier, a unique bucket across the entire S3 platform. Okay, so I'm going to clear. And now we'll use the AWS command line interface to get a listing of the S3 buckets. Okay, and to list the buckets in the S3 service for this account, I'll type AWS S3 LS. And I have one bucket with a unique identifier, a unique name. So let's copy that unique name by highlighting it and then right-clicking. Okay, and now I'll clear. Let's list the contents of the bucket. We do that by typing AWS S3 LS and the name of the bucket. So let's just right-click to paste the bucket name into the terminal and press enter. And it responds with one file. So there's one file in our S3 bucket with the unique name that we just described. Now, let's copy that file locally. So first I'll clear. And now I'll type AWS S3 CP. And now the name of the file or the object that I want to download. And I start that with S3:///. And I'll right click to paste the bucket name in. And I'll tack a / onto the end and the name of the file that we want to copy locally. It's called sample.txt. And for the output directory, I'll just specify dot, which is the current directory, and press enter. Okay, and it was successful. So AWS tells us that it was downloaded to the current directory. So first let's clear. And now if I do a cat of sample.txt, then I receive the message, hello S3 world, which is the content inside this file. So we've successfully created an S3 bucket. We've uploaded an object to the S3 bucket, and we've downloaded that object to the local machine by using the AWS S3 CP command. In this demo, we'll implement versioning with Amazon S3. It's best practice to implement versioning with Amazon S3 because it allows you to restore a version or roll back to a previous version if required. Versioning must be enabled at the bucket level. And by enabling version at the bucket level, basically you're changing the overwriting behavior. It will change the version of the object being uploaded and not overwrite any previous version. All right, I've signed into my AWS Management Console and I've navigated to the Amazon S3 console. Now I've got my browser set at 90% zoom, and I'm doing that so that we can see the entire row as we add objects to the bucket. So first, let's go ahead and create a bucket. I'll click Create Bucket, and for a name, I'll just call it Joe Bucket 999. Now remember that the bucket name has to be unique across the entire Amazon S3 service. Okay, scrolling down, we'll leave the rest of the values as they are and click Create Bucket. Okay, so the bucket was successfully created. In order to enable versioning, we can click the bucket, and now on the bucket page, right now we're on the Overview tab. Let's click the Properties tab, and front and center, there's a versioning tile. So let's click the versioning tile, and when the versioning dialog appears, click Enable Versioning and click Save. Okay, so now versioning is enabled. So now if I click to go back to the Overview tab, I'll see that I now have a Versions panel with a Hide and Show option. Okay, so let's upload a file 2 times to see how versioning works. So let's click Upload, click Add Files. Now I'll click developer.png, that's in my AWS projects subdirectory, and I'll click Open, and now I'll just click Upload. I'll do the same thing again by clicking Upload, click Add Files, do the same thing, select developer.png, click Open, and click Upload. Okay, so I only see one version with my Versions panel set with the option to hide versions. So if I click Show Versions, I'll see that I have 2 versions. So under Version ID, I see that each version has a unique identifier. Okay, back to the Versions panel and click Hide one more time. And now let's click to select the developer.png file, click Actions, scroll down and select Delete. And in the Delete Objects dialog, click Delete again. And now it appears that the bucket is empty. Well, let's go over to PowerShell. And now I'll delete the bucket by typing AWS S3 RB for remove bucket, S3:// Joe Bucket 999. Pressing Enter. And oops, we have an error. What does the error say? The error says that the bucket you tried to delete is not empty. You must delete all versions in the bucket. But if we go back to the S3 console and our bucket page, it appears that it's empty, but it's really not. Click Show, and that shows that we have the original 2 versions with the same version IDs, but now we've got a new version with a delete marker. Now if we delete the delete marker, so I'll click to select the delete marker, click Actions, click Delete, and now I'll click Delete in the Delete Objects dialog. And so now that delete marker is now gone, and the latest version is back to its original latest version. So now if I click Hide again, it shows that my developer.png file is back. Now, I can delete all the versions quite easily by clicking Show, and now I'll click beside Name to select all the files, and click Actions, and click Delete. Now if I click Delete in the Delete Objects dialog, I'll see that my bucket is now empty, even with the Show option selected. So now if I go back to Amazon S3 and I try to delete that bucket from here, it will work. So I'll click the PowerShell icon in the taskbar to go back to PowerShell. I'll type clear to clear my screen. And now I'll up arrow to bring that RB or remove bucket command back and press enter. And now I'm successful. So we've successfully implemented versioning with Amazon S3. And this again is a best practice because it allows us to restore versions if we accidentally delete them or roll back to previous versions as required. In this demo, we'll encrypt objects stored in Amazon S3 buckets. Okay, I've got Visual Studio Code open, and I've got a terminal prompt open in the bottom of the Visual Studio Code window. I have my readme.txt file open, and I'm going to highlight a couple of commands here. Now, I'm going to take advantage of the AWS S3 API commands to get and set my bucket encryption by default. So lines 4 and 5 contain the command that will get the bucket encryption status. And lines 8 through 10 will set the bucket encryption status by using a put-bucket-encryption command. So first, let's highlight lines 4 and 5. Let's get the current default encryption. So I'll highlight those two lines, right-click, select copy. Down in the terminal part of the window, I'll right-click to paste that in and press enter. And it should return an error, and it does. So we get the server-side encryption configuration not found error. Okay, so let's clear. And now lines 8 through 10. And this is against the bucket that I've created earlier called JoeBucket999. Okay, so I'll highlight lines 8 through 10. I'll right-click, select copy, and down in the terminal pane, I'll right-click to paste that command in. Now, what are we doing here? Well, we're using the put-bucket-encryption subcommand of the S3 API command to set the server-side encryption by default. So how do we do that? Well, we specify the --server-side-encryption-configuration flag, and we specify in JSON format the rule. And the rule is, and there's only one, it's apply server-side encryption by default. And the setting that I have is SSE algorithm AES256. So I'm going to set the default to AES256. And by setting a default scheme, what happens is when we upload an object to Amazon S3, if we don't specify the encryption type explicitly, then S3 will apply the default encryption on those objects. Okay, so let's press enter. And now let's clear. And now down in the taskbar, I'll click to bring up the S3 Management Console. So I'll click on the Firefox icon. I only have one bucket, so I'll click JoeBucket999 to drill down into my bucket. And now I'll click the Properties tab on the bucket page, scrolling down, locate the default encryption tile, and notice that it says AES256. So that is our default setting. I can set that default here as well by clicking on this tile, and it brings up the default encryption dialog where I can choose None, AES256, or AWS KMS. And we already set AES256, so we'll leave it. So that's our default encryption. Now, one other way that we can apply encryption to an object when we upload it to the bucket is by explicitly setting it when we use the upload utility here on the S3 console. So I'll click the Overview tab, and I'll click Upload, click Add Files. I'll just select the README. I'm in my AWS project subdirectory, and I'll click Open, and now I'll click Next. I'll click Next again to pass the Set Permissions page. I'm not going to change any permissions. And now I'm on the Set Properties page. Scrolling down, I have three options: None, Amazon S3 Master Key, and AWS KMS Master Key. If I choose AWS KMS Master Key, that results in a new field appearing, the Select a Key field, and clicking the down arrow to expand that, I've got AWS/S3 and Custom KMS ARN as my options. Now, the AWS Managed Customer Master Key is the master key for my AWS S3 service. And most AWS Managed Customer Master Keys are easily identified by their aliases, which have the familiar format that we can see here, AWS / and the service name. So in this case, S3. So let's choose AWS / S3. And I'll click Next, and I'll click Upload. Now, if I right-click on the file, in the fly-in, if I scroll down, I'll see that the encryption is AWS KMS. So why wasn't it AES 256? After all, that's the default. Well, recall that I said if you don't explicitly set the encryption level on the object when you upload it, then the default would apply. So instead, let's say, for example, that I'm on the AWS CLI and I just wanted to upload a file to my bucket and not specify a server-side encryption setting. So to do that, I would use the AWS S3 CP command. So let's do that. So I'll type AWS S3 CP readme.txt S3:// Joe Bucket 999 / and I'll press enter. And the AWS CLI responds with the uploaded file notification. So now let's go back over to the S3 console again, and I'll back out by clicking on the Amazon S3 link. I'll drill back down in by clicking on the bucket name. And now if I right-click the readme.txt file, I will now see that the encryption is set at AES 256 because we didn't set a specific encryption scheme when we uploaded the file this time from the AWS CLI. Okay, so we've successfully explored a couple of ways of setting the encryption on objects stored in Amazon S3 buckets. In this demo, we'll utilize Amazon S3 bucket policies. We can implement security policy on Amazon S3 buckets by setting up a bucket policy. Okay, so I've signed into Amazon Management Console. I've navigated to the S3 console. I've got a bucket named Joe Bucket 999. I'll click the bucket name to open up the bucket page. And now I'll click the Permissions tab. Now on the Permissions tab, I can select Bucket Policy. And now I can specify the policy. I can drill down and look at information about policies by clicking on the documentation link, or I can click to open the policy generator. Let's click Policy Generator. Okay, and that brings up the policy generator in a new tab. Now, step one, we're going to select the policy type, and the policy type is S3 bucket policy. Okay, now scrolling down, the statement includes the effect. Now, the effect is to allow or deny. What we're going to do here is we're going to deny the upload of any object that is not encrypted. So we'll click Deny. Now, the principal in this case is asterisk, and that applies to everyone. Now, the service is Amazon S3, and now select Actions. So I'll click the arrow to the right to expand the list. And what we're looking for here is Put Object. So let's scroll down the list and we'll find Put Object. We'll click to select Put Object. And now the Amazon resource name. So let's go back over to the S3 console tab and find our ARN. And it's beside Bucket Policy Editor, labeled ARN. So we'll highlight, right-click, select Copy, back over to the Policy Generator tab. And now we'll paste that in by right-clicking and selecting Paste. And now we also have to specify a / and an asterisk because we want this to apply to all objects in the bucket. Now we'll need to add conditions. So let's click Add Conditions. And for our add condition, what we're going to do is we'll specify the condition equals null. And the key, now for the key, we're going to specify the encryption header. That's the server-side encryption header. And we'll set that value to true. Okay, so let's click the down arrow. We'll scroll down and we'll find the S3:x-AMZ-server-side-encryption. And for value, again, we'll specify true. And we'll click to add that condition to our policy. Okay, now click Add Statement. And now we'll click Generate Policy. And our policy appears in the policy JSON document. Let's highlight the entire thing. Right-click, select Copy. Back over to the S3 Management Console. We'll paste that into the policy area. And we'll click Save. Okay, so now let's go back out by clicking Amazon S3. Now we'll click the bucket name again to drill down into the bucket. And now we'll click Upload. So let's try to upload a file. So I'll click Add Files. I'll select the readme.txt file. Click Open. Click Next. Click Next again. And now we're on the Set Properties page. Scrolling down, I'll see that I have 3 encryption settings that I can choose from. We'll leave none selected. Click Next and then click Upload. And we see that we have an error. So let's click on the error and we'll click View Details. And it says that the upload was forbidden. Why was it forbidden? Well, it was forbidden because we didn't encrypt it. So our bucket policy worked. So we defined a policy here that basically will not allow any objects to be uploaded unless they are encrypted. So let's try that again, and we'll encrypt it this time. So let's click Upload, Add Files, click readme.txt, click Open, click Next, Next again. Now on the Set Properties page, scrolling down, we'll select Amazon S3 Master Key, and we'll click Next, click Upload, and 1 success. So we were successful uploading that time because we explicitly set the encryption. All right, so we've successfully implemented security policy on this Amazon S3 bucket such that no object can be uploaded to this bucket unless it is encrypted. In this demo, we'll configure an Amazon S3 bucket to host a static website. Okay, I've got Visual Studio Code open, and I've got a couple of files here. Just a very basic index.html file that basically has a title. And in the body, I have a message that says, "Hi, I am Joe Developer. You have found my S3-website-1." And an image is splashed on that page as well. And then I also have an error page. And the error says something went wrong. Okay, so now let's go over to the browser where I have the S3 Management Console open. Let's start by creating a bucket. So I'll click Create Bucket. For a bucket name, I'll specify Joe Bucket 999. We'll leave the region at US East. And now scrolling down, we're going to set the bucket settings for public access. Now right now I'm blocking all public access, and that's by default. But I'm going to click to uncheck that because we do want to provide public access. After all, we want the public to be able to access our static website. Okay, so scrolling down, notice the warning, turning off block all public access might result in this bucket and objects within becoming public. And then it specifies that unless it is required for specific verified use cases like static website hosting. So let's click I acknowledge, click Create Bucket, and success. Now let's click the bucket name. Now let's click Upload, and let's upload a couple of files. We'll click Add Files. And in my AWS Projects subdirectory, in the File Upload dialog, I'll select all files by highlighting them, and I'll click Open, and I'll click Upload. Okay, so all 3 files have now been uploaded into my bucket. Now let's go over to the Properties tab, and on the right-hand side, locate the static website hosting tile. We'll click on that. Scrolling down, this is our endpoint. We'll need that, so let's copy that right now. So we'll highlight it, right-click, select Copy. Now we'll select the Use this bucket to host a website option. And for the index document, we have to specify the index document. And in our bucket, we uploaded an index.html file. So let's specify that. And the same with the error.html file. Okay, and scrolling down, click Save. And now we have bucket hosting configured. All right, so let's open a new tab. Right-click, select Paste and Go, and an error, 403 forbidden. Okay, so why is that forbidden? Well, it's because we have to explicitly set a bucket policy to allow all of our users the get object privilege. Okay, so back over to Management Console. So I'll click the S3 Management Console tab. I'll click the Permissions tab, click Bucket Policy, scroll down, select Policy Generator. And for step 1, the type of policy is S3 Bucket Policy. We're going to leave the effect at Allow. And principal is asterisk. That's everyone. We want this to apply to everyone. And for select actions, click to expand, and then scroll down and find Get Object. And now click Get Object. And now we need the Amazon resource name. Back over to the S3 Management Console tab. Let's highlight the ARN. Right-click, select Copy. Back over to Policy Generator. Let's paste that in. And again, we'll tack on a / asterisk at the end because we want this to apply to all objects. So we're ready. Just click Add Statement and then Generate Policy. And in the Policy JSON document dialog, highlight the policy, right-click, select Copy. Now let's go over to the S3 Management Console tab. Right-click, select Paste. Paste that policy in, and now click Save. All right, and now we see a notification that this bucket has public access. So we're aware of that, and we want to allow public access to the bucket to serve up our static website. Okay, so now let's go over the tab labeled 403 Forbidden. And now our endpoint hasn't changed. So if we refresh, we should see the index.html page. So let's go ahead. And there's our index.html page. Success. Now let's try the error. So we'll tack on / and we'll specify, for example, sales.html. And that was an error, so we see the error.html message, something went wrong. Okay, so we've successfully configured an Amazon S3 bucket to host a static website. In this demo, we'll enable cross-origin resource sharing. Cross-origin resource sharing, or CORS, allows client web applications loaded in one domain to interact with resources in a different domain. And we can provide CORS support to our Amazon S3 bucket-based static websites. Now I've got my Visual Studio Code editor open. I'm looking at index-cors.html. This is my first website's HTML document for its main page. Now everything here is pretty simple HTML until you get down to the script tag between lines 15 and 25. And specifically on line 18, where we're using the fetch function to fetch a resource from JoeBucket9999 website, and that resource is called other.html. And what does other.html look like? Well, if I click the other.html tab, here it is. This is a message from the other.html page from S3-website-2. Okay, so now let's go over to S3 Management Console. So down in the taskbar, I'll click the browser icon to open up S3 Management Console. So I've got my two websites set up based on JoeBucket999 and JoeBucket9999. So JoeBucket999 is my first site. So I'll click on the bucket name, and I can see that this is the one that has the index-cors HTML document. So this is the one that's going to be trying to access the second website. Okay, now clicking to go back to Amazon S3. If I click JoeBucket9999 to drill down into this bucket, I'll see that it has the other.html. So this is my second website. Now if I click Properties, click Static Website Hosting, I'm going to highlight the endpoint, right-click, select Copy. I'll open a new tab, and just to demonstrate that this is actually working, click Paste and Go. So this is the second website. So it's working. Now the first website. So the first website should be able to access the other.html on the second website. So now let's go back to Amazon S3. By clicking Amazon S3 at the top of the page, we'll click Joe Bucket 999, Properties, Static Website Hosting. Let's highlight the endpoint, right-click, select Copy, open a new tab, right-click, select Paste and Go, and this looks okay, but we're missing a message down below the image, and that message is what's going to be populated from the other.html. Now, a good way to troubleshoot is with the developer tools, and Firefox developer tools are awesome. So just press Ctrl-Shift-I to open developer tools, and we can see right away that the cross-origin request was blocked, and we can see why. Reason, CORS header is missing. Right, so we have to configure CORS support for our second website. So now let's go back down to Visual Studio Code. So I'll go and click the VS Code icon on the taskbar, and now I'll click to open the CORS-CFG.xml, and here is my CORS configuration. So the CORS rule tags define the CORS rule, and the CORS rule is defined as follows. Allowed origin, and that is the first website. And then the allowed method is get, the maximum age in seconds is 180, and the allowed header is authorization. So let's copy this entire CORS configuration. So I'll highlight everything, right-click, select Copy. Now we have to go and configure that second website so that it will allow the first website to access resources. So down in the taskbar, I'll click the browser icon. I'll go back to S3 Management Console tab. Scrolling up, I'll click Amazon S3. Now I'll drill down into Joe Bucket 9999. Now on the Joe Bucket 9999 page, click the Permissions tab. Then I'll click CORS Configuration. And in the CORS Configuration Editor, I will right-click, select Paste, and click Save. Okay, so now I've configured CORS on the second website. So now let's go back to S3-Website-1 tab. We'll close the developer tools, and now let's refresh. And success. There is our message. So we've successfully enabled cross-origin resource sharing on our Amazon S3 bucket-based static websites. In this video, we'll explore AWS data consistency. One important consideration when choosing Amazon S3 or Amazon EBS storage service is the consistency model employed by each storage option. Amazon S3 uses read after write consistency for puts of new objects only, while EBS uses read after write consistency for all operations. Amazon S3 offers eventual consistency puts that overwrite and for deletes in all regions. Updates to a single key are atomic. What all this means is that, say for example, one were to put an object in order to update an existing object and then immediately attempted to read the object, either the old data or the new data may be read. One important note, since Amazon S3 does not support object locking, if there were two put requests arriving simultaneously against the same key, the put request with the most recent timestamp prevails. So, if this presents a problem, we may need to build an object locking mechanism into our applications. Amazon S3 was designed to use this level of consistency because of the consistency, availability, and partition tolerance theorem, also known as CAP theorem. It states that one can highly achieve just 2 of the 3 dimensions for any specific storage design. What is partition tolerance? Partition tolerance may be considered as storage durability. Amazon S3 is designed for high availability and durability, which entails multiple copies being maintained across multiple facilities. So, consistency is the design trade-off. When an object is put, it is put into 3 locations. What this means is that one will experience either a marginal increase in latency with the read after write consistency of a put, or eventual consistency with put, update, or delete operations. We don't know which facility will be serving a file when performing a get on an object. If there was a recent write to an object, perhaps it hasn't propagated to all 3 facilities yet, and so a read right after may serve either old or new object. Let's consider the characteristics of an eventually consistent read versus consistent read. With eventual consistent read, you have possible stale reads. With consistent read, there is no stale read. With eventual consistency, we have low latency, whereas with consistent reads, we have high latency reads. Then again, with eventual consistency, we have high throughput reads, and consistent reads provide lower throughput reads. In this video, we'll explore Amazon S3 performance criteria. Amazon S3 implements some actions by default in order to help attain a very high level of performance. Amazon S3 scales automatically to thousands of requests per second per prefix based on steady state traffic. Amazon S3 will automatically partition prefixes to accommodate the increase in request rates within hours. To optimize Amazon S3 mixed workloads or get-intensive workloads, it's crucial to be familiar with best practices for performance optimization. Considering mixed request types, if requests are usually an assortment of get, put, delete, and get bucket or list object requests, then choosing appropriate key names for objects results in better performance with low latency access to the Amazon S3 index. With get-intensive workloads, if the majority of the workload involves simple GET requests, the Amazon CloudFront Content Delivery Service may be a good choice to use with the S3 service. How keys are named in Amazon S3 can impact data access patterns, which may in turn have a direct impact on an application's performance. Best practice dictates that we design applications for performance from the very beginning. Applications are typically expected to grow over time. If we expect the application to grow to more than around 1,000 requests per second, then we should consider using a 3 or 4 character hash in key names. A naming hash may improve the performance of heavy traffic applications. Since object keys are stored in an index in all regions, if we see that we're constantly writing the same key prefix repeatedly, a good example of this being a key with the current year, then all of the objects will be close together within the same partition in the index. When the application sees an increase in traffic, it attempts to read from the same section of the index, which results in decreased performance as Amazon S3 attempts to spread out the data for higher levels of throughput. However, before embarking down this path, it's a good idea to ensure that your application can handle naming hash. We add randomness by placing the hash at the beginning of the key name. This will help ensure that the data is spread across different partitions ultimately accommodating a higher level of throughput while avoiding a reindexing slowdown when exceeding peak traffic volumes. An important feature of Amazon S3 is the Amazon S3 transfer acceleration. It optimizes throughput when transferring relatively larger objects across greater geographic distances. Amazon S3 transfer acceleration uses Amazon CloudFront edge locations, leveraging Amazon's global content delivery network to upload data to the closest edge location. Although there is a small fee for using transfer acceleration, if the transfer speed isn't any faster than over the public internet, then no additional charges apply. Other performance considerations include using multi-part uploads because the upload API allows us to upload large objects in chunks, which really means uploading in parallel. We should also consider range gets, which are similar to multi-part uploads, but apply to downloads of large objects. If we're downloading a large object and tracking the offsets, we can use range gets to download the object in multiple parts in parallel, which may result in a performance improvement. Of course, there's Amazon CloudFront, which, as we've seen, can help us realize lower latency and higher throughput. There's TCP window scaling, which can improve network throughput by supporting larger window sizes. And TCP selective acknowledgement can improve recovery time after large volumes of packet losses. In this demo, we'll work with Amazon S3 Glacier. Amazon S3 Glacier provides a management console which you can use to create and delete vaults. However, all other interactions with S3 Glacier require that you use the AWS command line interface or write code. Okay, so I've opened PowerShell and I have AWS CLI installed on this machine. So the first thing that I'm going to do is I'm going to get the account ID because I'll need that in order to create a vault. And to do that, I'll type AWS STS get-caller-identity, pressing enter. And from here, I can grab my account ID. So I'll highlight my account ID and right-click. Now, to create a vault, I'll use the AWS Glacier command, create-vault. First, I'll clear, and then I'll type AWS Glacier create-vault --vault-name, my vault, --account-ID, and I'll paste my account ID in. Okay, I'm pressing enter, and now I have my vault created. Now from here, I can describe the vault. Okay, so first I'll clear, and now I'll use the describe vault command to describe my vault. And to do that, I'll type AWS Glacier describe-vault --vault-name, and the name of my vault is my vault, and --account-ID, and I'll paste my ID in. Now, I actually don't need the ID. If I use a hyphen here instead of the account ID, it will still work. It will use the current account ID. But I'm using the account ID for this demo, just so that you understand. And that provides me with a description of my vault, including the number of archives in it, the size in bytes, and so on. Now, in order to add an archive to your vault, you can use the Glacier upload-archive command. Now, first I'll clear, and the structure of that command is AWS Glacier upload-archive --account-ID. We need the account ID, then the vault name, which is my vault, and then with the --body parameter, I specify the archive or file name that I want to archive in S3 Glacier. Now, I'm not going to run this command because in order to remove an archive, it can take days. But at least we get to see the structure of the command, and we get to see how to create archives and interact with S3 Glacier for anything other than creating or deleting a vault through the CLI or by writing code. Okay, so we've successfully created a vault and looked at archiving data on Amazon S3 Glacier. In this course, we've examined the design and implementation of cloud storage on AWS using a number of AWS storage services, including Elastic Block Storage, EBS, Elastic File System, EFS, and Amazon Simple Storage Service, S3, as well as S3 buckets. We did this by exploring scenarios for EC2 instance stores, AWS EBS for implementing block storage, and implementing a content delivery network, or CDN, with AWS CloudFront. We looked at how AWS implements EFS for file storage and sharing, and S3 for object storage. We looked at various methods for the migration of application and business data to AWS storage, how to create, use, and version AWS S3 buckets, and how to encrypt objects stored in S3 buckets and S3 bucket policy implementation. We also looked at how to generate a static website using S3 resources, how to use cross-origin resource sharing or CORS. We looked at AWS S3 consistency models and S3 performance management, and how to archive data using AWS S3 Glacier. In our next course, we'll move on to explore how to use the various types of available AWS database services, including in-memory data stores, Amazon RDS, and SQL and NoSQL databases. In this video, we'll explore AWS Cloud Database offerings. There's a wide-ranging collection of databases on AWS Cloud, each designed for a specific purpose or set of use cases. In addition, there's also the option to install, configure, and manage our own database platform on an Amazon EC2 instance, and to support the migration of existing databases to the AWS Cloud, Amazon offers the AWS Database Migration Service. Now, let's have a closer look at the different types of database offerings on AWS Cloud. First, AWS offers data warehousing databases in support of analytics operations against huge volumes of data. Graph databases are ideal for managing datasets that are highly connected. In-memory data store databases are used for workloads requiring real-time level of performance and caching of workloads. And ledger databases are specialized for use in managing the cryptographically verifiable history of transactions. Relational databases are typically used for transactional workloads. Non-relational databases, which are fast and flexible, support web-based applications. And time series databases are for workflows involving time series data. As mentioned, relational databases operate on structured data, and typical use cases involve transactional applications like logging e-commerce transactions and storing structured data. Amazon offers Aurora and Relational Database Service, or RDS, for this purpose. NoSQL and non-relational databases support internet scale applications and can operate on structured or unstructured data. One example of the type of application that's a good fit for this type of database is Duolingo. This is a mobile language training app with millions of users and the need for a flexible data schema. For that, Amazon offers Amazon DynamoDB and Amazon DocumentDB. Duolingo uses Amazon DynamoDB. Now, data warehousing supports analytic workflows, and they're very cost-effective. For example, much less costly than traditional solutions. And for that, we have Amazon Redshift. In-memory data stores like Elasticache support Memcached or Redis-based cache. And graph databases, again, for highly connected data, for example, news feeds, and for that we have Amazon Neptune. For time series data, we have Amazon TimeStream, for example, to manage data streaming from IoT devices. And ledger databases. Ledger databases are specialized and are used for keeping a verifiable and immutable log of mission-critical transactions, for example, banking credits and debits. For that, we have Amazon QLDB. So, a very wide-ranging selection of databases on AWS Cloud. In this video, we'll explore relational databases from Amazon. A relational database stores sets of data items that have predefined relationships amongst them. The data is organized in sets of tables comprised of columns and rows. And basically, tables are used to store information about the objects represented in the database. Now, 4 key characteristics about relational databases. First, relational databases support the use of structured query language, or SQL, for interacting with the database, including reading data, adding, modifying, and deleting data, for filtering data, and for the overall process of managing the data. Relational databases incorporate integrity constraints that force data integrity in the database. And this refers to the completeness, the accuracy, and the consistency of the data. That's data integrity. Some typical constraints include primary keys, foreign keys, unique constraints, not null constraints, check constraints, and default constraints. These integrity constraints help ensure that business rules are enforced at the table level, which in turn preserves the accuracy and reliability of the data. Most relational database systems also support custom code triggers that are executed based on an action or event in the database. Relational databases use transactions. A transaction is essentially one or a sequence of SQL statements that are executed as a single logical unit of work. Transactions are also atomic in that they are all or nothing events. The entire transaction must successfully complete as one single unit. If for whatever reason one of the sequence of statements can't complete, then the entire transaction is rolled back or canceled. So the outcome of any transaction is either a commit or a rollback. All transactions in a database are ACID compliant, meaning that transactions are, again, atomic, but it also means consistent, isolated, and durable. Atomicity means that each statement in the transaction executes successfully or the entire transaction is invalidated. Consistency requires that when data is written to the database as part of a transaction, it must observe and follow all defined rules and restrictions like triggers, constraints, and cascades. Isolation ensures that all transactions are independent and isolated from each other. And durability means that as a transaction successfully completes, changes written to the database are permanent. AWS offers both managed and unmanaged relational database services. A managed database service is one in which AWS takes care of the administrative tasks, including the provision of hardware, the configuration of the database, replication, throughput capacity planning, software patching, and scaling the database. Amazon RDS is a fully managed relational database service, while the EC2 service provides us with the ability to install, configure, and manage virtually any specific relational database system. But we are responsible for the administration of the unmanaged database. In this video, we'll explore Amazon's fully managed relational database service. As a fully managed relational database service, Amazon RDS takes on the responsibility of managing difficult, time-consuming administrative overhead, and it also simplifies or streamlines other important tasks like procurement. For example, when planning hardware requirements, the memory, CPU, storage, and IOPS are separate options, which means that they can be scaled independently and only as required. RDS handles configuration tasks like managing backups, automating patches, monitoring for and detection of failures and faults, as well as recovery. Now, with backups, we can manually design and operate our own backup and restore process, or we can choose RDS Automated Backup Restore, which is seamless, reliable, and efficient. With respect to security, if we enable the encryption option for an RDS database instance, AWS takes care of that for us. And we can make the database a highly available one by having AWS take care of a synchronous secondary instance as a failover resource when there are problems. In addition, some relational databases on AWS can take advantage of read replicas for read scaling. Currently, Amazon RDS supports 6 common database engines. Amazon Aurora, which is a MySQL and PostgreSQL compatible database engine. Then there's Oracle, Microsoft SQL Server, of course PostgreSQL and MySQL, and MariaDB, which is a fork of the MySQL database engine. Now let's consider some RDS features. As mentioned, RDS takes care of patching as part of the periodic maintenance process, which we can stipulate to take place during a maintenance window of our choosing. Typically, patching involves patching the underlying operating system or database engine version. RDS offers vertical scaling. In this case, we can choose the number of virtual CPUs and memory for the underlying infrastructure based on workload, and AWS seamlessly handles the vertical scaling for us. If our RDS instance is in a multi-availability zone configuration, then a standby database is scaled first, then a failover happens to the new configuration. Vertical scaling is ideal for write-intensive applications. RDS offers storage scaling with several configurable options, including 3 different storage types: general purpose SSD, provisioned IOPS for input-output intensive workloads, and magnetic storage, although the latter is provided more for backward compatibility, and in fact AWS recommends instead to use SSD solid-state drives or provisioned IOPS for RDS workloads. Horizontal scaling is implemented using read replicas, which is ideal for read-heavy applications. Read replicas create read-only copies of the master database, enabling us to place any reads onto the read replicas. Keep in mind that replication is asynchronous, so this is most suitable for applications that don't require real-time, up-to-date data. Currently, RDS, MySQL, PostgreSQL, and MariaDB engines are limited to 5 read replicas, Amazon Aurora to 15 read replicas, while RDS, Oracle, and SQL Server database engines don't support read replicas. Now, there are 2 ways to implement backups in RDS. We can back up the database instance with automated point-in-time backups and database snapshots. With automated backups, RDS takes a full daily snapshot of the data, and then after each daily snapshot, it captures transaction logs as changes are being written to the database. The default retention period for a backup is 7 days, with an option to increase up to 35 days. With the automated process, you can restore up to a specific second within the retention period. With user-initiated snapshots, we can back up our database instance and restore to that instance at any time. In this manual process, the backups are retained until we explicitly delete them. Best practice involves taking a final snapshot before removing an RDS instance. RDS supports multi-availability zone configurations with a primary and secondary database instance. Updates are replicated to the standby synchronously to a different availability zone in a multi-AZ configuration. With this configuration, RDS automatically fails over to the standby in the event of planned maintenance or a database instance or availability zone failure. RDS uses AWS Key Management Service for AES 256 encryption to protect data at rest. And for encrypting data in transit, RDS generates an SSL certificate for each database instance for connecting an application to the instance. It also supports transparent data encryption for Oracle and SQL Server. we can leverage identity and access management to authenticate to the database instance. This way, we can centrally manage access to database resources rather than storing user credentials in the database itself. In addition, the IAM feature encrypts network traffic to and from the database with SSL. IAM authentication is only available for some versions of MySQL and PostgreSQL. Amazon RDS integrates with CloudWatch to monitor the database using alarms, which we can configure with various metrics. We can have CloudWatch notify someone responsible, like the administrator, when a failure occurs, and with this integration, it means we have audit, error, general, and slow query logs for our RDS database instances. In this video, we'll explore Amazon non-relational databases. Non-relational databases are typically used for internet-scale applications which don't commonly implement complex queries. A NoSQL database is a non-relational database which is optimized to support scalable performance and work with flexible, schema-less data models. NoSQL databases are known for how easy they are to develop with, and they're ideal for low latency applications and are also known for their resilience. Reviewing SQL versus NoSQL databases reveals that for data storage, SQL uses rows and columns. NoSQL uses key value pairs, documents, wide column, and graph objects. For schemas, SQL is fixed, NoSQL is dynamic. For querying, we use structured query language with SQL databases, and with NoSQL databases, we are more focused on a collection of documents. With respect to scalability, SQL databases scale very well vertically, while NoSQL, they scale very well horizontally. SQL supports transactions. With NoSQL, that support can vary, so it's very flexible. For consistency, with a SQL database, we have strong consistency, but with NoSQL database, we can have eventual and strong consistency. So again, quite flexible. NoSQL databases are ideal for big data, for mobile, and for web applications that have higher database scaling and responsiveness requirements than that provided by traditional relational databases. With horizontal scaling and streamlined data structures, NoSQL databases commonly provide better response times and are much simpler to scale than relational databases. The different types of NoSQL databases vary in how they store, access, and structure data, and because of these differences, they are more suited to specific use cases. Columnar databases, for example, are designed for optimally reading and writing columns of data rather than rows of data, because it significantly reduces disk I/O and the amount of data that you must load from disk. They are very well matched to use cases involving analytic queries. Document databases store semi-structured data as documents, typically JSON or XML documents. They are very flexible, accommodating a varying document schema, in contrast to traditional relational databases, which must work on a fixed schema. Graph databases store vertices and directed links, which are known as edges. These vertices and edges may have properties associated with them, and graph databases may be built on top of either SQL or NoSQL databases. In-memory key value store is a NoSQL database incorporating in-memory caching, which helps to improve application performance by storing important items of data in memory, resulting in extremely low latency access. This type of database is optimized for read-heavy workloads like gaming or social networking applications, and for compute-intensive workloads like recommendation engines. In this video, we'll explore Amazon DynamoDB. Amazon DynamoDB is a fully managed cloud database service. It's fast and flexible, it provides reliable performance, it automatically scales throughput capacity, and consistently provides single-digit millisecond latency at any scale. These characteristics make it ideal for applications that require low latency throughput, schema flexibility, and scalability, like mobile, gaming, and Internet of Things applications. DynamoDB automatically spreads data and traffic for its tables over multiple servers to meet throughput and storage requirements. All data is stored on solid-state drives and is also automatically replicated across multiple availability zones within an AWS region. So what does that mean exactly? Well, it means high availability and data durability. To keep DynamoDB tables in sync across AWS regions, DynamoDB can use global tables. With global tables, we specify what AWS regions we want the table to be available in. Then DynamoDB creates identical tables in these regions and propagates ongoing data changes to all of them. Core components of DynamoDB includes tables. A table is a collection of items, and each of those items has a set of attributes. DynamoDB uses a primary key to uniquely identify each item in the table. The primary key can be composed of a single attribute known as a partition key, or a composite primary key, which is comprised of two attributes, a partition key and a sort key. An item's partition key is also known as its hash attribute, while the item's sort key is known as its range attribute. In some situations, we may wish to perform queries based on attributes that are not a component of the table's primary key. For that, we use a secondary index key. A secondary index key contains primary key attributes and secondary or alternate key attributes, as well as an optional subset of attributes from the base table known as projected attributes. There are two types of secondary indexes in DynamoDB: local secondary indexes, which have the same partition key as the base table, but a different sort key, and global secondary indexes, which have a different partition key and sort key from the base table. We can define as many as 5 global and 5 local secondary indexes per table. In this video, we'll explore in-memory data stores on Amazon. In-memory data stores are primarily used for caching and for applications with real-time workloads. In-memory key value database options on AWS include instance stores on Amazon EC2, Amazon Elastic Block Store, or EBS, and the fully managed non-relational service Amazon ElastiCache. In caching, data is usually stored in hardware like RAM for fast access. The purpose of a cache is to improve the performance of data retrieval operations. Caching can also help reduce load on the back-end database tier. It can help reduce or eliminate database hotspots. Caches provide high read throughput since we're generally talking about reading from memory, and caching provides data access with very low latency since, again, we're talking about data that is accessed and stored in memory. There are two main primary strategies with caching, and they are lazy loading and write-through. But first, let's define a couple of important terms used when referencing caching. So, a cache hit occurs when information is requested and the cache contains the information requested. A cache miss happens when information is requested and the cache does not contain the information requested. Okay, so lazy loading as a caching strategy involves loading data into the cache only when necessary. So, say for example, our app makes a request to the cache. If there's a cache hit, then the data is retrieved. If there's a cache miss, the data is then retrieved from the data store all the way back to the data store and then stored in the cache. Lazy loading has the distinct advantage of caching only data that is requested, but on the downside, a cache missed penalty results in a database query, and only then is the cache updated. Write-through caching involves adding data or updates to the cache whenever there is a write committed to the database. The positive here is that the data in the cache is never outdated, but the disadvantage is that there is a write made to the cache every time there is a write made to the database. In addition, much of the data may never be used. So with this scenario, you may end up paying for storage that is unnecessary, and if data is updated on a frequent basis, it may result in cache churn, which is a condition where the cache is constantly updating. In-memory data stores, utilized as a NoSQL data store, have a very flexible architecture, and as such, they are not only very efficient databases, they are primarily built for scalability. As a distributed cache, organizations can scale applications as required to address spikes in demand, which can be more cost-effective than disk-based stores. And of course, there is also the benefit of the extreme performance. The ElastiCache service simplifies the deployment, operation, and scaling of in-memory cache. ElastiCache can improve the performance of web applications by retrieving information from managed in-memory caches. ElastiCache supports both Redis and Memcached caching engines. This is a fully managed service, and as such, reduces administrative overhead while implementing this type of service. For example, the ElastiCache service automatically detects and replaces failed nodes. Now, Amazon DynamoDB Accelerator, or DAX, is a fully managed, highly available in-memory cache that's built specifically for DynamoDB. Amazon says, in fact, that response times with DAX are measured in microseconds at millions of requests per second. DAX manages cache invalidation, data population, and cluster management. In addition, developers don't need to modify application logic to use DAX since it's compatible with DynamoDB API calls. When using DMS to migrate data, the service connects to the source data store, reads and then formats the data source for use in the target data store. Meanwhile, cached transactions and log files are written to disk. The migration process involves a series of tasks, and each task can consist of 3 primary phases: loading all existing data, applying any cached changes, and performing continuous replication as required. When using DMS to migrate data, the service connects to the source data store, reads and then formats the data source for use in the target data store. Meanwhile, cached transactions and log files are written to disk. The migration process involves a series of tasks, and each task can consist of 3 primary phases: loading all existing data, applying any cached changes, and performing continuous replication as required. AWS Data Migration Service supports both homogeneous and heterogeneous database migrations. For heterogeneous migrations, DMS uses the AWS Schema Conversion tool, which is used to automatically convert the database schema and most database objects like views, functions, and stored procedures from the source database to a format that the target database is compatible with. It can also scan an application's source code for SQL statements and convert them as part of the migration process. And the Schema Conversion tool also performs cloud-native code optimization, which involves converting legacy SQL Server and Oracle functions to corresponding services on AWS. In this demo, we'll install the Python SDK for AWS, also known as Boto3, and the PyMySQL client library for interacting with MySQL from Python code. Okay, to get started, I've opened my browser. I just wanted to highlight the location of the Python download. So that's python.org/downloads. And from there, you can download the Python version and install it. It's a very simple, straightforward install. However, in this demo, we need to install the Python SDK and PyMySQL. And to do that, down on the taskbar, I'll click to go to my Visual Studio Code editor. In the Visual Studio Code editor, I've got a terminal session opened. And now from here, I'm going to check first of all what Python version that I have. And to do that, I'll type Python -- version and press enter. I have Python 3.7.4 installed. Okay, so I'm going to clear after every command, and I won't say that every time. I'll just type clear and press enter. Okay, now to upgrade my Python package manager, pip. And to do that, I'll type Python -m pip install -- upgrade pip. And the -m flag just tells Python to run the library module as a script. So I'm kind of using pip to upgrade pip. Okay, pressing enter, and it tells me that I'm already up to date. Okay, so now let's install Boto3, the AWS SDK for Python. And now to do that, I'll just type pip install Boto3, and I'll press enter. Okay, now some requirements were already satisfied, but eventually it installed Boto3 version 1.13.21. Okay, now let's install PyMySQL. And to do that, again, we use the Python package manager, pip, and I'll type pip install PyMySQL. And pressing enter, and done. So let's use pip to show what versions of the Boto3 client and the PyMySQL client installed. And for that, I just type pip show and the names of the packages that I want to check. So Boto3 and PyMySQL, and press enter. So now I can see what version of the AWS SDK that I have installed on this machine. 1.13.21. And scrolling down, I also see the version of PyMySQL is 0.9.3. Okay, so we've successfully installed the AWS Software Development Kit for Python, known as Boto3, and the PyMySQL database client that we'll use later for accessing MySQL. In this video, we'll generate a security group for an Amazon RDS database. Okay, I've signed in to my AWS Management Console and navigated to the EC2 dashboard. Under Resources, I have 3 security groups. If I click Security Groups, I'll see that I have 2 default security groups and 1 web server group. I want to add a security group for interacting with Amazon RDS. And to do that, I'm going to use the AWS SDK for Python, that's Boto3, and I'm going to get a Boto3 client, and I'm going to create the security group in code. Down on the taskbar, I'll click to bring up my Visual Studio Code editor. In Visual Studio Explorer, I'll click to bring up the rds_create_sg Python file. And let's see what we're doing here. So in line 1, first I'm importing Boto3 to bring in the software development kit. Then from lines 4 through 6, I define some variables. I've got my security group name, my description, and my IP CIDR address. Now your IP CIDR address will be very different than mine, but make sure if you just want to be able to connect from your specific client machine to tack on a /32 at the end. Now in line 9, that's where I create an EC2 client. So I call the client method on Boto3, and I'm getting an EC2 client. Now, from lines 12 down through 15, basically this is where I create my security group. So I call the create security group method on the client that I created earlier. I pass the description for the security group and the name for the security group. Then I'm going to print out the response from the create security group method on line 15. On line 18, I call the authorize security group ingress method on the client. I pass the CIDR IP address, the from port, the group name, the to port, and the IP protocol. Then I print out a message saying security group successfully created. Okay, so down in the terminal, to run this program, I type Python rds_create_sg.py and press enter. So I got the response back from the create_security_group method. And then after adding the rules, the message security group successfully created is splashed to the terminal. Okay, down on the taskbar, let's click to bring up my browser window. And now I'm still in my security groups panel. So I'm going to refresh to see that we have a brand new security group named rds-mysql-sg. Let's click on it. And now scrolling down, let's take a look at those inbound rules. So basically, the type is MySQL/Aurora. It's TCP protocol. The port is 3306. And the source for my inbound rules. And I will only allow this IP address to connect. Now, clicking to view the outbound rules, all outbound traffic is allowed. We didn't specify any restrictions there. Okay, so we've successfully created a security group for Amazon RDS from Python code using the AWS Software Development Kit for Python. In this video, we'll create an Amazon RDS database instance. To get started, I've signed into my AWS Management Console, and I'm going to navigate to the RDS console. So in Find Services, I'll type RDS, and I'll click the RDS link. And this brings me to the RDS dashboard. Under Resources, I have 0 database instances. If I scroll down, under Create Database, I'll click Create Database. Okay, this brings me to the Create Database page. Now, I can choose the Easy Create method, in which everything is handled by default, or the Standard Create method. I'll use the Standard Create method to step through the options. So first, the engine options. For this demo, I'm going to create a MySQL database. So I'll click MySQL. And for the edition, I'll click the down arrow, and I'll scroll down and I'll select the most recent edition, MySQL 8.0.19. Now, if you're concerned about limitations or issues, you should review the Known Issues Limitations page by clicking the Known Issues Limitations link. Okay, so let's move on. Now, for templates, I can choose Production, and this is for high availability and performance. And then Dev Test, and we'll go with Free Tier. So I'll click Free Tier. Under Settings, for Database Identifier, this is where we type our database instance name. For me, I'm going to call mine MySQL-TestDB. So I'll just type this in. Okay, under Credential Settings, the master username, I'll use my first initial last name. I won't auto-generate a password. I'll enter my own master password. And confirm password. Scrolling down for database instance. Now, if I'd chosen Dev Test or Production, I would have much more to choose from as far as the options go. I could have standard classes or memory optimized classes, but because I chose Free Tier, I only have the burstable classes. So clicking the down arrow to expand the options list for the machines that I can choose, I've only got the db.t2.micro. All the rest are grayed out because we're creating this in the free tier. So I'll click to select the db.t2.micro. Scrolling down, for storage, we have general purpose SSD. The other option is to use provisioned IOPS. We'll just use general purpose SSD. For allocated storage, the minimum is 20 gigs. We'll leave it as is. Scrolling down for auto scaling. Now we can choose storage auto scaling, which provides dynamic scaling for us. We'll choose to disable storage auto scaling. So I'll uncheck the enable storage auto scaling checkbox. Now scrolling down, because I chose the free tier, I can't select the multi-AZ deployment. Okay, so scrolling down now under connectivity, the VPC is my default VPC. I will leave that as is. Now I'll click to expand additional connectivity configuration. The subnet group I'll leave as is. Now I want to make sure that this is publicly accessible because later on I'm going to use an external client to connect to the database. So I'll click yes. And for the security group, I'm going to choose an existing security group that I've already created for RDS. So if I click the down arrow to expand my options, I'll choose RDS-MySQL-SG. And I'll click the X in default to remove it. For availability zone, I really don't have a preference. And for database port, 3306 is the standard database port. For database authentication, I'm going to leave password authentication selected, but note that I can also choose, even on the free tier, password and Iam database authentication. But again, I'll leave password authentication selected. Now, expanding additional configuration, this is where I can enter an initial database name. And for my initial database name, I'll specify testDB. Scrolling down, I have the option to uncheck enable automatic backups, but I will leave this selected because I want to enable automatic backups. Under retention period, 7 days is the default. However, I can choose up to 35 days if I desire. For the backup window, if I click select window, now I can choose a backup window. But I'm fine with the way that it is. So I have no preference. Now, under monitoring, I can click to enable enhanced monitoring. I won't enable enhanced monitoring at this time. But notice I've also got the ability to publish error, general, and slow query logs to Amazon CloudWatch. I won't do that for now. And scrolling down, I see my maintenance window. Again, I have no preference. I will leave it as is. I can also enable deletion protection, and this protects from deleting the database when this option is enabled. I'll leave it disabled. And scrolling down, I'll click Create Database. Okay, and now if I scroll over, I'll see that my database currently has a status of creating. Now, this can take a few minutes to launch your database, so just be aware. Okay, so the database has now been successfully created. So if I scroll back over to the right, I'll see the status now says available. If I click the link for the database, that takes me to the database page where I can get all kinds of detail about my database instance, including the endpoint, which I'll need to connect over the internet. Okay, so we've successfully created an Amazon RDS database. In this demo, we'll install MySQL Workbench and we'll configure it to connect to an RDS managed MySQL database. I've opened my browser and navigated to mysql.com/product/workbench. On the middle of the page, find and click Download Now. On the MySQL Workbench download page, make sure that the operating system is correct, and it is. Scroll down and locate the Windows MSI installer for MySQL Workbench Community and click Download. Now on the Login Now or Sign Up for a Free Account page, let's just skip the process altogether and click No Thanks, just start my download. In the opening dialog that appears, click Save File. And now it appears that the download has been completed. So I'll click the download icon in my browser's toolbar. And I'll click to open the Community MSI installer. Now in the Open Executable File dialog that appears, click OK. And the Setup Wizard opens. Now I'll click Next on the Welcome page. I'm not going to change the destination, so I'll click Next. leave complete selected, click Next, and click Install. If a user account control dialog appears, click Yes, and the installation proceeds. Okay, so setup has completed. Leave the Launch MySQL Workbench checkbox selected and click Finish. Workbench starts. Now we need to create a new MySQL connection. I'll click the plus icon beside MySQL Connections, and now the Setup New Connection dialog appears. In this dialog, I'll give the connection a name. I will just call it RDS MySQL Database. The connection method, standard TCP/IP, is fine. The host name, now for the host name, we're going to specify the endpoint from our RDS MySQL database. So now let's go down to the taskbar. I will click on the browser again to bring the browser back up. I'm going to close the MySQL Community Downloads tab by clicking the X on the tab. And now I'm in my AWS console for RDS. Now I'll click the MySQL-testDB database link and scroll down under Connectivity and Security, find my endpoint. I will highlight my endpoint, right-click, select Copy. Now back on the taskbar, I'll click to bring up MySQL Workbench setup again. And now in the host name, I'll highlight the local host and I'll press Control-V to paste that in. Now the port is fine. The username is actually first initial last name. And now password, I can store my password in a vault, or I can clear all passwords. So first, I'm actually going to click Test Connection. This will come up and ask me for my password. So in the Connect to MySQL Server dialog, I'll enter my password. I'm going to click to save the password in the vault and click OK. And now the MySQL Workbench dialog appears telling me that I've successfully made the MySQL connection. So I'll click OK. And now that we've confirmed the MySQL connection, let's click OK. And now on the RDS MySQL database tile, I'll click to open this connection. OK. MySQL Workbench opens with my RDS MySQL database connected. Now this is a great administrative and development tool for MySQL databases. So we've successfully installed MySQL Workbench and we've configured it to connect to an RDS managed MySQL database. In this demo, we'll use the AWS Python SDK called Boto3 to create a SQL table and add records to it in an Amazon RDS MySQL database. Okay, I've got my Visual Studio Code editor open. I'm going to click to open my Python file. And this is my RDS create table Python file. So let's go through the code here. So first, my imports. I'm importing the AWS SDK, that's on line 1, Boto3. And then on line 2, I'm importing an interface so I can communicate with the database, and that's PyMySQL, and I'm importing that as MySQLDB. From lines 5 through 9, I'm defining my variables. For example, my RDS identifier, which is simply my RDS database instance. I've got my database name, which is testDB, my username, the user password, and my RDS endpoint. Now I make the connection from lines 12 through 16, and I get a cursor on line 17, which will allow me to navigate through the database. So for my connection, I call the connect method on line 12 with MySQLDB. That's the PyMySQL interface, recall. I specify the host, my username, the password, and the database. Now scrolling down, from lines 20 down through 32, I'm creating my table. And I'm doing that within a try block so that I can handle any errors. So basically, I'm going to create a table named students. The student will have a student ID, and that's an auto increment value, an integer auto increment. I've got name, city, country, and I'm specifying the primary key on line 27, student ID. Then I print a successful message on line 28. Then I handle the exception in case there was an error from lines 29 through 30. And then finally, I close my database connection on line 32. Now, scrolling down, I have to make another connection to the target database and get another cursor. So that's from lines 35 through 40. Then from lines 43 down through 55, that's where I'm adding information or adding data to my table. So I'm inserting 4 students into my table. So I have to specify the SQL statement. So that's insert into students, the name, city, country, and the values. And then from lines 45 through 48, I'm using cursor.execute to execute the SQL statement with the values that I'm going to add into the database. Then I do a db commit to commit the transaction. Then on lines 51 through 53, I'm basically handling the error in case something went wrong. And finally, I'm closing the database again on line 55. Okay, so let's run this and see what happens. And to run it, down in my terminal session, I'll type Python and the name of the file, which is just rds_create_table.py. I'll press enter. And I see the message table successfully created and then students successfully added. All right, well, let's go verify. That's why I've installed MySQL Workbench. I want to be able to interact with my database externally so that I can verify the operations that I'm performing. So down on the taskbar, I'll click to open MySQL Workbench. I've got a connection to my SQL database already. I use the same endpoint. So I'm just going to refresh the connection. So beside schemas, I'll click the refresh icon. And now I see that tables has something under it. Let's expand tables. And there's the student table. So if I expand the student table, it shows me that I've got some columns, student ID, the primary key, name, city, and country. And so now if I want to view that data, I can do so in the query editor. So I'll click inside the query editor. I'll type use and the name of my database, which is testdb. And then I'll type select star from students to select everything from students. Now click the execute icon in the toolbar. And there are the students that I added into my table. All right, so we've successfully used the Python SDK for AWS to create a SQL table and add records to it in an Amazon RDS MySQL database. In this demo, we'll query a table in an Amazon RDS MySQL database using the execute method and the AWS SDK for Python. Okay, I have Visual Studio Code open. I'm going to click to open my RDS query table.py file. And let's examine the code. So lines 1 and 2, I'm importing Boto3, the AWS SDK for Python, and PyMySQL as MySQLDB. And PyMySQL, again, that's the interface for Python into MySQL databases. Then from lines 5 through 9, I define the variables that I need for this little program, including the RDS identifier, which is just the MySQL database instance on Amazon RDS, the database name, the username, the password, and the RDS endpoint. From lines 12 to 17, I'm making a connection to the target database using my variables, and on line 17 specifically, I get a cursor so that I can navigate through the database. And then from lines 20 down through 30, I'm querying the table within a try block. So on line 21, I define my SQL statement, which is just select star from students. Then I call the execute method on my cursor, and I pass it my SQL statement. And I'm setting another variable, res, with the results from cursor.fetchAll. then I print a querying table message, then I print the response, which is res. And then lines 26 through 28, basically I'm handling any exceptions. And then finally on line 30, I close my database connection. Okay, so let's see this in action. So down in the terminal session, I'll type Python and the name of the file, which is just rds_query_table.py, and I'll press enter. Okay, and the message came up, querying table, and I see the results from the query. So basically it returned all of the students that I have in the students table. All right, so we've successfully queried a table in an Amazon RDS MySQL database. In this demo, we'll delete an RDS database and its associated security group using the AWS SDK for Python. Okay, with my Visual Studio Code editor open, in the VS Code Explorer, I'll click to open the rds_del_db.py file. Now, in this code, in lines 1 and 2, I'm importing the Boto3 AWS SDK, and in line 2, I'm importing the JSON library. I'll need that for formatting some data later on. Lines 5 through 7, I define my variables, including my RDS identifier, my security group name, and my security group ID. Now the security group ID is blank because we're going to retrieve that later in code. On line 10, I generate an RDS client. So I do this by calling the client method on Boto3 and passing the RDS specification. Now, from lines 13 down through 20, this is where I'm deleting my RDS instance. So in line 13, I define a variable res, which is short for response, and that's equal to the call to the client with the delete_db_instance method, and I pass the instance identifier as well as the skip final snapshot. I'm specifying that equals true. Then I print please wait while we terminate the RDS instance, and I format that as the RDS identifier. Then line 17. Line 17 introduces a concept called a waiter. Now, just some background on waiters. Consider there are several requests in AWS using Boto3 or any SDK for that matter that don't result in an instant response. There are many scenarios where we need Boto3 to wait for the request to complete before moving on to other parts in our script. Typically, because subsequent operations in our code have some dependency on the long-running process being completed, for example, deleting the database. So that's what we're doing here on line 17. I'm basically calling the get_waiter method on the client, and the waiter that I'm specifying is the db_instance_deleted waiter. Then on line 18, I call the wait method on the waiter, specifying the identifier and the maximum number of attempts. Finally, on line 20, I print that it's been deleted. So once it has been deleted successfully, it will print that it's been deleted. Now, what happens is that the service polls the describe_db_instance status every 30 seconds until a successful state is reached, and an error is returned after a specified number of failed checks. Okay, so now scrolling down, line 23, I call the client method on Boto3 again, this time specifying the Ec2 client. So I'm creating an Ec2 client. Then lines 26 through 27, I basically set up my response, and I call the describe_security_groups method on the client. Then line 27, that's where I specify the security group ID, and I have to format it using the JSON dumps method. Now on line 30, I'm ready to delete the security group with the security group ID. So I call the delete_security_group method on the client, and then I print a security group deleted message. Okay, so let's go ahead and run this. So down in the terminal session, I'll type Python and the name of my file, which is just rds_del_db.py. Now, before I run this, one more thing. I had to delete the database instance first because you can't delete the security group when an interface is attached to that security group. So I have to delete the database first, then I can delete the security group. Okay, so let's go ahead and run this. So I'll press enter. And we see the please wait while we terminate the MySQL-testDB RDS instance message. Now I can fast forward through this because this is a video, but be aware that this can take a couple of minutes. Now if I head on over to Aws Management Console, so down in the taskbar, I'll click to bring up my browser. And now I will click the dashboard and I'll refresh. And it says 0 database instances. So if I click to bring up the database instances, I'll see that the database instances have not been found. So let's go back over to Visual Studio Code. Okay, and now the message came back. The MySQL-testDB RDS instance has successfully been deleted, and we just verified that. And the security group has also been deleted. Well, let's go and verify that again. So back over to the browser. So I'll click the browser icon in the taskbar. Now I'll click to expand services and I'll go over to EC2. And now I'll click security groups to see that the security group for my RDS instance has now been deleted as well. So we've successfully deleted the database and the security group using the AWS SDK for Python. In this demo, we'll create a table in an Amazon DynamoDB database. Okay, I'm signed into my AWS Management Console. I'm going to go to the DynamoDB service. So in the Find Services field, I'll type DYN and I'll click on DynamoDB. That brings me to the DynamoDB dashboard. Now, if I choose to create a table here, so I'll click Create Table. I specify the table name, the primary key, and if I want a composite primary key, I click to Add Sort Key. And then the rest of the table settings are by default using the default settings. So that means no secondary indexes, auto scaling capacity set to 70%, and encryption at rest with default encryption type. I can also specify some tags here and then click Create. Now, we're going to do the same thing in code. So down on the taskbar, I'll click my Visual Studio icon to bring up Visual Studio Code. And in VS Code Explorer, I'll click the dynamo_create_table.py file to open it so we can go over the code. All right, so in line 1, I'm importing Boto3, that's the AWS SDK for Python. Then on line 4, I define a variable table_name and set it to students. On line 7, I'm getting a reference to the DynamoDB resource by calling resource on Boto3 and passing DynamoDB. Then the interesting part happens from lines 10 down through line 36. This is where I'm creating my table. Now, we use the create table method or operation to create a table in Amazon DynamoDB. When we make the call to create table, we have to specify the table name, the primary key attributes and data types, and the throughput settings for a provisioned table. So that's what I'm doing on line 11. I'm setting up my table name. Then lines 12 through 31, I'm specifying my primary key attributes and data types. So line 14, my attribute name, student ID, that's my partition key. So I specify the key type as hash. Then on line 18, the attribute is name, and that's my sort key. So the key type is range. Then in the attribute definitions, student ID is a string, name is a string, and then the provisioned throughput. Now, when using provisioned mode, which is free tier eligible, we must specify the initial read and write throughput settings for the table. This is the amount of read and write activity that the table can initially support. DynamoDB reserves sufficient resources to address our throughput requirements based on these values. Now, we can modify these settings later, or we could just enable DynamoDB auto scaling and allow DynamoDB to manage the settings automatically. But here I've set the read and write capacity units both to 10. Okay, now on line 37, I splash a relevant message to the console. Then line 38. On line 38, I call wait underscore until underscore exists on my table. I'm doing this because I have to wait until the table exists. Now, I strictly don't have to because really I'm not doing a lot after that. But if I was, for example, adding data to the table, I would have to wait until that table exists, obviously, until I can add data to the table. So that's why we have these so-called waiters. So once the program has waited until the table exists and gets the positive that it exists, then I print that the table is ready. Okay, so let's go ahead and do this. So down in the terminal session, I'll type Python and the name of my file, which is just dynamo_create_table.py, and press enter. And I see the first message, please wait while we create the student's DynamoDB table. Now this can take a few seconds, so just be aware. Okay, so now it comes back and says the student's table is ready. So let's go over to Aws Management Console and check this out. So down in the taskbar, I'll click the browser icon to bring up the Aws Management Console. I'll expand services here and select DynamoDB under History to go to the DynamoDB dashboard. Now I'll click Tables in the left nav menu, and there's my student's table. I'll see the partition key consists of student ID, and the sort key is name, and they're both strings. So exactly as we specified. So we've successfully created a table in an Amazon DynamoDB database using the AWS SDK for Python. In this demo, we'll add records to a table in a DynamoDB database with the put item method. Okay, I've signed into my Aws Management Console and I've navigated to my DynamoDB tables list. Now, I've got one table that I recently created. It's a student's table. Its status is active. The partition key is student ID. The sort key is name. I've got a total read and total write capacity of 10 each. And the encryption is default encryption. Right now, I've got no items in this table. So let's go down to the taskbar. I'll click the Visual Studio Code icon to bring up Visual Studio Code. Now in the Visual Studio Code Explorer, I'll click to open dynamo_add_records.py. Okay, so let's have a look at this code. So in lines 1 and 2, I'm importing Boto3, that's the AWS SDK for Python, and I'm importing the JSON library. I'll need that for formatting some data that's going to be output. Now, in line 5, I define a variable table_name, and its name is students. That's the table that we just looked at. Now, on line 8, I'm creating a resource service client so that I can perform some operations on my table. So for that, I call the resource method and pass DynamoDB. Then, in line 11, I get a reference to the table. That's the students table. And then from lines 14 through 21, that's where I'm adding the item to the table. So I call the put item method on the table, and I specify the item with the student ID, the name, the city, and country. Then finally on line 24, I'm going to print the JSON response. So I'm calling the dumps method from the JSON library, and I'm passing the response. I'm indenting by 3, and I'm sorting the keys. Okay, so let's go down to the terminal session, and we'll type Python and the name of the file, dynamo_add_records.py, and I'll press enter. And very quickly, it came back. And the JSON response includes this HTTPS status code of 200, so everything seems to be okay. So let's go back to Aws Management Console and the DynamoDB tables list. I'll click the browser icon in the taskbar. I'll click Students to open up my Students table. And over in the right pane, I'll click Items to see that I now have one item. So I've successfully added that item to the table using the put item method. In this demo, We'll run a query against a NoSQL DynamoDB table using the query method. I've signed into Amazon Management Console and I've navigated to the DynamoDB dashboard. In the left nav menu, I'll click Tables to reveal that I have one table in this database. It's Students. If I click Students, and in the right-hand pane I click the Items tab, I'll see that I have one record. And that one record has a student ID of 1000, the name is Bob, the city is Fredericton, the country is Canada. Okay, so let's do a query against this table and see if we can get a match on this record. So down in the taskbar, I'll click the Visual Studio icon to bring up Visual Studio Code, and in the VS Code Explorer, I'll click the dynamo_query_table.py file, and let's have a look at this code. So in line 1, I'm importing Bot03, that's the AWS SDK for Python. Now, in line 2, I have to import the key class from bot03.dynamodb.conditions. And I have to do that because in order to query a table, we need to import this class because the key class is used when the condition is related to the key of an item. Okay, so line 6, I define my variables, and I have just one, that's table_name, and it's students. In line 9, I'm creating a resource service client for DynamoDB by calling resource and passing DynamoDB. Then in line 12, I get a reference to the table, and then we perform the query on line 15. So in line 15, I call the query method, and I specify the key condition expression equals key, and what's the key name? Well, it's student ID dot eq for equals 1000. Then on line 18, I'm checking to see if there were no items. And if there were no items, I want to print a message indicating that. And otherwise, I'll print the JSON response. Okay, so let's go down into the terminal session. I'll type Python and the name of the file, which is dynamo_query_table.py, and press enter. And success. So I've successfully queried a NoSQL DynamoDB table using the query method. In this demo, we'll use the batch writer method to write data in a batch process to a DynamoDB table. Okay, I've signed into AWS Management Console. I've navigated to my tables listing in the DynamoDB console. I have one table. I'll click to open the students table. In the right pane, I'll click the items tab to reveal that I have but one record. Okay, so now let's go down to the taskbar. I'll click the Visual Studio Code icon to bring up Visual Studio Code. And in the Visual Studio Code Explorer, I'll click to open dynamo_batch_writer.py. Okay, so let's examine this code. So first, in line 1, I'm importing Bot03, that's the AWS SDK for Python. Then I'm importing the UUID library, and I'll need that to uniquely identify a student by giving them a unique student ID. On line 5, I define my variables. I have but one, table_name, and it's students. In line 8, I'm creating a resource service client for DynamoDB. Then in line 11, I get a reference to the table that I'm going to be working with. Then from lines 14 all the way down to line 31, that's where I'm actually writing data to the table. Okay, now if you're loading a lot of data, we can use the dynamodb.table.batchWriter method to accelerate the process and at the same time reduce the number of write requests made on the service. The batchWriter method returns a handle to a batchWriter object which handles buffering and sending items in batches automatically. The batchWriter also automatically handles any items that went unprocessed, resending them as required. We simply have to call putItem for any items that we want to add. So let's see what we're doing here. So in line 14, I specify with table.batchWriter as batch. Then I'm setting up a for loop So I'm going to create 5 items, one for each iteration through the for loop. So now in line 16, I call put item. And the item is going to be composed of a student ID with a call to UUID. Then for the name key, I'm going to add the string value of the counter just to have a unique name key. Then the city and country are going to remain the same. Now, starting on line 24, I do the same thing, but with a different name, if you will. So in this case, it's going to be Jane, and I am appending the string of the counter to Jane's name, and her city is Toronto, and the country is Canada. So all in all, we're going to be adding 10 records here. Then, on line 32, I print a successfully wrote and the number of records that were written to the DynamoDB table. Okay, so let's go down into the terminal session and type Python and the name of the file, which is dynamo_batch_writer.py, and press enter. And the program comes back and tells us that it successfully wrote 10 records to the student's DynamoDB table. So let's go over to Aws Management Console. So in the taskbar, I'll click the browser icon. Now I have the table open. I'll refresh by pressing the refresh icon. And that reveals that I do have the additional items that I added to the table. Okay, so we've successfully used a batch writer against a NoSQL DynamoDB table. In this demo, we'll scan an Amazon DynamoDB table using the scan method. I've signed into Aws Management Console and I've navigated to the DynamoDB console. Okay, I've got my students table open, and I'm just going to do the scan here first. So in the table, basically, I select Scan, and then I click Add Filter. Now, the attribute here is country. So I'll enter country, and it's a string, and the condition is equals, and for the value, we'll enter USA. And now we'll click Start Search. And that reveals 5 items. So if I scroll down, I'll see all 5 items. Okay, now let's replicate this in code. So down on the taskbar, I'll click the Visual Studio icon to bring up Visual Studio Code, and I'll click the dynamo_scan_table.py file in Visual Studio Code Explorer to open the file, and let's examine this code. So in line 1, I'm importing Bot03, the AWS SDK for Python. On line 2, we're importing the attr class from bot03.dynamodb.conditions. Now, we're importing this class because we need to use it whenever there's a condition in our scan that's related to an attribute of an item. Okay, so in line 3, I'm importing the JSON library. I'll need that to format the response. In line 6, I define my table name, and that's students. In line 9, I'm creating a resource service client. In line 12, I'm getting a reference to the table. And then on line 15, this is where I'm actually performing the scan. So I call the scan method, and I specify a filter expression equal to that attr, and I'm looking at the attribute country .eq USA. Now I'm printing a message on line 16 indicating that I'm getting the total count in the table. And then on line 19, I'm just handling the possibility that there is no match. And then on lines 22 and 23, I'm printing out the total item count and the JSON response. Okay, so now down in the terminal session, I'll type Python in the name of the file, which is dynamo_scan_table.py, and I'll press enter. Okay, and it comes back. And notice that these are exactly the same items that were returned when we did the scan in the DynamoDB console. All right, so we've successfully performed a scan against an Amazon DynamoDB table using the scan method. In this demo, we'll delete a table from the DynamoDB service. Okay, I've signed into AWS Management Console and I've navigated to my DynamoDB console and I've got my students table open. Now, to delete a table here, it's very easy. Just click Delete Table, and in the Delete Table dialog that appears, we're asked to confirm that we really want to delete the table. Note that the Delete All CloudWatch Alarms for this table checkbox has been checked by default, and the Create a Backup before deleting this table is unchecked by default. If we do want to create a backup before deleting this table, we just check the checkbox. I'll leave it unchecked though. Now, as a way to verify that we really do want to delete it, we have to type delete in the text box and then click delete. Now, I'm going to cancel here. We're not going to delete this table here. I'm going to go down into the taskbar. I'll click the Visual Studio Code icon to bring up Visual Studio Code. In the Visual Studio Code Explorer, I'll click to open the dynamo_delete_table.py file. Now let's examine this code. Very short little program. So basically we're importing Boto3, the AWS SDK for Python. Then I'm importing the JSON library for formatting purposes. Then on line 5, I specify my variable, and it's just one variable, table name, and it's students. In line 8, I'm creating a low-level service client by calling client on Boto3 and passing DynamoDB as the service that I want to interact with. And then on line 11, this is where I'm calling delete_table. And with this method, I just have to specify the table name. And then on line 12, I'm printing the JSON response. So down in the terminal session, I'll type Python and the name of this file, which is dynamo_delete_table.py, and press enter. Okay, and the table status is deleting. So now if we quickly go over to AWS Management Console, so I'll click the browser icon in the taskbar. Now I see that the students table is still open. So let's click tables now. And so if I scroll over in tables, I'll see that nothing has changed. The table still is here. Now if I refresh, I'll see that now the table has been deleted. Okay, so we've successfully deleted a table from the DynamoDB service using the delete_table method. So in this course, we've examined the AWS database offerings as well as how to work with both relational and non-relational databases. We did this by exploring the different database offerings on AWS. We explored relational and non-relational databases and in-memory data stores. We explored the options for migrating data and databases to AWS. And we also explored how to generate security groups for Amazon RDS and create a MySQL database on Amazon RDS. We explored how to create and query a SQL table using Amazon RDS and how to delete a database instance and associated security group. We looked at how to create and add records to a NoSQL DynamoDB table. We explored how to query a NoSQL DynamoDB table and use batch writer against NoSQL DynamoDB table. And we also explored how to scan and delete an entire NoSQL DynamoDB table. In our next course, we'll move on to explore the AWS Elastic Beanstalk service, including how to utilize its deployment options for configuring reliable, scalable, and highly available applications on AWS Cloud.